College of Architecture, and I've been teaching in the Architectural Engineering Design Studios. I'll give you just a brief overview of where the capstone team has been and where we're going. We started the month of September by looking at the AEI competition results from last year, including the first place team and integration last year, our esteemed group in the back of the room here. So students familiarize themselves with previous competition entries. We also looked at this year's AEI competition brief, so we had an idea of what we're supposed to be doing in the competition this year. We also took a wild field trip to Milwaukee to actually visit the site, which is the subject of the competition, and also the institution, Growing Power, which is essentially the client for the competition. We also had students in the month of September look at the Living Building Challenge. And Matt Grokoff, where's Matt? There's Matt. So Matt's been helping out. He's our local expert on the Living Building Challenge, and all the students are familiar now with the tenets and principles of the Living Building Challenge. We also spent the month of September looking at some optimized systems that we felt might be appropriate for Growing Power and the site in Milwaukee. We spent the month of October first faced with a decision. Do we essentially follow the design of the baseline building that comes with the competition, or do we redesign the building in response to the client and the site? Students elected unanimously to redesign the building, so we spent the month of October basically doing architectural work and also setting us up for the engineering systems that would complement the architecture. So the month of November, this past month, we've been focusing very specifically on the engineering systems, the integration of those engineering systems, and also developing the architecture in concert with the engineering systems. So here we are, December 9th today. We have completed to date, I think, a good schematic design, something that everyone will understand what it is we're doing, how we're responding to the client, how we're responding to the Living Building Challenge. We have, I think it's exactly 5 weeks from today in which to get to 100% design development. We're in schematic design today, 100% design development in 5 weeks. We have another 3 weeks and a couple of hours to actually submit all our work for the competition. We have about 3 weeks to prepare 5 reports. Each report is about 45 pages. That includes graphics and text. And there are 5 categories in the competition. Integration is the #1 and most important category. There's structural, electrical, mechanical, and construction. And we have to have a report for each of those 5 sections. So 2 tasks tonight for the group here. One is to provide some valuable constructive criticism and suggestions for how students can develop their work to 100% DD by mid-January. And the second is really relative to our program overall. Everyone has some rubrics in hand. So there are 2 rubrics. One is in LTU blue. I'd like everyone to be able to fill this out by the end of the evening. This is an assessment for the entire project team. We have 7 students, 1 large project. So the blue one is for the entire team. And then you have 3 Christmassy color, the red and green. 1 sheet for each of the 3 primary teams. So 1 sheet for the structural team, 1 for the electrical team, 1 for the mechanical team. They'll be presenting in that order, and they'll introduce themselves by name, so there won't be any confusion. Just make sure you circle or note which team is which page. The simplest thing you can do is just circle in this gradation of, I think it's outstanding to poor. Just circle in the gradation for each category. You're more than welcome to write comments. You're more than welcome to write questions down on these sheets. Ultimately, we're going to collect these. It's part of our LTU assessment and also our AVET accreditation. That's why you're filling out the sheets. Any questions so far? I know I'm doing a quick summary here. So tonight, the project team, there are 7 students, so introduce themselves. We're going to have essentially 4 different, well, I guess 4 different chapters to the presentation. The first one will be a broad overview, and then we'll pause a little bit and ask questions. make comments. Then we'll have the structural team present. Same thing, we'll pause after their presentation, questions, comments. Then the electrical team, then the mechanical team, and then we'll have concluding comments and remarks. That sound clear? Sound exciting?
Mm-hmm.
Let's go. Let me introduce the team. Maybe just introduce all of them, or each other.
All right, I'm Diana Brazier.
And I'm Tom Ozium.
Andrea Beatty.
I'm Hayan Audi. Stephen Gunther.
Rebecca Tritt.
Israel Ortiz.
Perfect.
The first part of our presentation is the AEI competition itself, going through the handbook and the guidelines that they gave us and the baseline building they provided us as a baseline design. So first, the AEI competition guidelines. There was a whole handbook that we went through, and we picked out certain criteria that we thought should drive our design. And among those guidelines were implementing energy efficient, sustainable solutions, utilizing alternative energy resources. It was also the integration of disciplines was very important in how they optimized energy and environment conservation, as well as the building has a twist this semester where we have to holistically design for an alternative location as well as our main location with minimal changes to the design as a whole. And then, like Ralph previously said in his introduction, that the engineering systems should complement each other while enhancing the architecture. And there's 5 competition categories: integration, structural, mechanical, electrical, and construction.
So the baseline building is a program and was mostly greenhouses with supportive spaces for education and community gathering. So there was plants, vegetables, and herbs that we looked at. Hydroponic fish tanks were also something that the AEI competition wanted us to glance at, along with a demonstration kitchen that was in the programming and an indoor-outdoor marketplace. So our baseline building site is in Milwaukee, Wisconsin. Growing Power Institution itself, zoom in on the site. Sorry. That's what our site currently looks like. Where you see the existing buildings is the east side of the site where the marker is, and then a lot of the stuff on the left side of the site gets removed for the competition, as you can see here on the site plan that they issued to us. So the baseline building they proposed was a 5-story vertical greenhouse building, and it would be situated like that on the site. And they decided to have parking on the west side of the site and farmlands to the north to complement with the greenhouses that are already existing. This is a 3D view of the baseline building that they gave to us, and you can see how their building fits on the site, and it will compare well to what we have later. So the basement level actually is mostly storage and food storage spaces, just for service of the Growing Power Institution. The first level is the market and food processing. So this is where most of the community space would be for selling. The second level has a gathering space that would seat 453 people, and then also a growing space on the front south side of the building. The third level has all the classroom spaces for education, along with the adjacencies to growing and some university offices that would help. The Growing Power Administration offices would be located on the 4th level, and with growing spaces to the south, and then also growing spaces above it on the 5th floor. And this is a section. So again, the basement, just to recap, was mostly storage and food processing. Level 1 had market and food processing. Level 2, gathering and growing. Level 3, education and growing. level 4 was the growing power administration, and the top level also had growing space.
The Living Building Challenge is a standard that's comprised of 7 different categories, or called petals, and they are subdivided into 20 different imperatives. These imperatives challenge everyone to move the design from being merely just less bad into actually going into a regenerative project.
So the reason why we chose to take on this challenge was we're actually designing it around a natural process in the greenhouses and the growing power, like actual growing power institution. So they're also moving towards creating a positive impact for the environment and society around it. So we figured, why wouldn't we look into a program that actually guides us in this direction, which ended up being the Living Building Challenge itself.
The first petal is the place petal, and the intent of this petal is to limit the growth in order to protect green areas, and it also dictates that the team must include opportunities to integrate agriculture in every building that is designed. For the water, 100% of the water requirement for the building must be collected on site from rainwater, and from rainwater or from or utilizing a closed loop system, and all the water collected or must be recycled if it's going back out to the site. For the energy, 100%, 105% of the total energy that the building utilizes on a yearly basis must be collected from renewable energy sources, and there's absolutely no combustion allowed. There's also scale jumping is allowed, so if another building on the site can produce more than what it needs, it could supply a different building on the site in order for the entire for the group of building to meet that 5% minimum over what's needed for the energy for the entire site. The health and happiness petal is aimed to its main focus is to look at it's aimed to look at what is absolutely required in the building and in the spaces in order to create a robust and healthy environment, rather than looking at all the possibilities or all the things that could go wrong in the building. So it focuses on only incorporating what is absolutely needed. And there's also a biophilic requirement, which requires all the teams to incorporate natural environment or green plants in all the spaces in the building.
The materials petal is pretty much in pushing you to use environmentally friendly materials that are locally sourced, so you can use them, or you're also supposed to use them efficiently so you don't burden the environment with waste as well. So everything must be net zero for waste. Here is a map. We're actually required to use a certain percentage of materials around us. It's actually by cost, overall cost. So 20% of our building cost has to come within 500 kilometers of our site, 30% within 1,000. And then we have consultants that can be within 2,500 kilometers, and then the rest, another 25% of our cost can come from 500 or 5,000 kilometers away. The equity petal just pushes you to make the building equal to people regardless of their age, their race, their disabilities. Really emphasize ADA requirements as well. The beauty pedal is simply about human delight and making it an enjoyable building to be in, while also inspiring other people to build another more structures and design around being environmentally friendly, as this is this challenge.
Adrian and I are going to talk about growing power. So growing power is a institution that was established by Will Allen. It's basically meant to empower urban community by providing a place where they can get some healthy alternatives for food, rather than some of the less expensive, empty calorie foods that are more abundant in urban areas. So Will Allen is the son of sharecroppers, and he felt a connection with the community because of that background, that he can create a facility that he can kind of teach some of the ideals that he absorbed from this farming background. So ideas like patience, being intentional. If you plant a certain seed, you're going to get that kind of crop. And then really understanding natural integration connections that are in nature, and seeing how we all connect with that. So this is the actual facility right here. Right now they conduct weekend hands-on workshops where they do some teaching of farming techniques. They basically produce 40 tons of vegetables per year on 3 city acres. They have 500 egg-laying hens. They provide eggs for the community, as well as an apiary. So they do a lot of community outreach as well. The whole idea is to have it a teaching and collaboration facility. So the vision that Growing Power has is basically based on simplicity, integrity, and it's really a community organization. It's almost like a community center.
Well, we also, in September, we visited Growing Power, because it's one thing to, Israel did a really good presentation for us before we actually visited the site in Milwaukee, but to visit it and to research it are 2 different things. So on a really cold, rainy 2 a.m. morning in September, we all piled in a van and drove to Milwaukee, and these are some of our pictures from the site. So from our experience, actually being on the site and interacting with the people there, we're able to see that the systems are designed very simplistically. You expect there to be maybe more elaborate systems, but these greenhouses are very old, and the rainwater collection is very old, and the hoop houses are movable, and they can put things wherever they need to, so it's very flexible. The community is just as important as a system as the rest of the rainwater and the power and every other system at the site. So this top picture over here is a picture of their market in the front of the building, and then below is a picture of the inside of the market. So it's very simple, but it works very well for the people that are there. And there's also lots of character inside the greenhouses and on the site. So there's everyone that works there also eats the food, and there are kids from the community that they employ as volunteers, and then when they graduate from high school, they're given jobs right away if they want them. So it's a very important part of this community. And so these are some other pictures of our visit. It's one cohesive system, so the plants, the energy, the animals, the people, they all work together as one system, and which was very apparent to us once we went.
And basically Will Allen, he has a lot of ideals and philosophies that really drive him. Pick up a shovel, get your hands dirty, and let's begin. That's really what it's all about. He uses a metaphor about what you can do with worms and how they heal soil. And he sees people as being able to be healed and being able to be changed to be better themselves. So really the whole vision of Growing Power is to, well, what they want right now is just a larger facility to be able to basically share the philosophies of sustainability and community within the context of a building that is influenced by just natural systems.
So like Ralph mentioned earlier, we as a team decided early on that we were going to reconstruct the entire building and how we thought was going to be best fit for growing power as a whole. So when we started, it was, how do you design an urban farm just based off someone else's idea? Well, we looked at current farms and how they operate. And a lot of these farms have been around for hundreds of years, so obviously they're doing something right. So how do they respond to plants, animals, people, and the climate conditions around them? And then also, what is growing power now? And like Andrea and Israel talked about, they're full of life, they're energetic. They're simple, but they're not too simplistic. And then we've also looked into what the client actually envisioned for the property. And he wanted it to be a community center. He wanted to have a strong connection to the street. And he wanted a place for people, where people could go and learn and basically take anything that they had at Growing Power and take it back to their house and do it themselves. And so a couple of years ago, Israel, Tom, and Andrea all studied the Kimball Art Museum for another one of our classes. And when we were looking back at some of the different stuff, it seemed like a very fitting building to follow in our redesign of the building. There was a strong connection to modular construction. There was very specific public, private, and circulation spaces, and everything worked together as a whole and was integrated with one another. And so some of the goals we had was to not over-design the building in both architecture and engineering, the systems, but we also wanted to try to really reduce the height from 5 stories down to 3 stories. Because by doing that, we could change the type of construction that we were, and it fit more with what is currently around the site. It's low residential right now, and so a 5-story commercial building is pretty hard to just plop into place. And we also wanted to maintain the linear flows that are on site. There's a lot of east-west direction, and all the greenhouses currently that have been around for hundreds of years on the site are east-west in direction. So this is just a recap of, this is their existing structure, and then this is our redesign. We reduced it from 5 down to 3 stories and still maintained all the same programmable spaces throughout the building. So their current site, as you can see, it's all their greenhouses and everything are currently here, and then anything that's movable is over on the west side of the site. So the proposal was to keep the original greenhouses where they were, but put a long, in the north-south direction building right in the middle, and then parking, get rid of all kinds of growing area for the parking pad. And then on the far west side of the site, there was nothing going on. So with our new site proposal, we pulled the building, elongated it, and pulled it closer to the street so that we could maintain all of the growing area behind the building, and we incorporated the parking as part of the building itself. And so the basement, we kept all of the storage spaces in the basement, and the existing building did not have much mechanical electrical space at all. So we put all the MEP and storage spaces in the basement. And then on the first floor, we have the market and all of the necessary processing and utility spaces that Growing Power needs to operate every day, like their coolers and their workshop, and where their volunteers can go. Along with parking is on the west side. And then on the second floor, it steps back a bay because we still kept with the same idea that was originally presented to us, was stepping back so that we can maintain long greenhouses in the space. And we have all growing along the south side of the building, and then education, office, and the large gathering space. So we basically took floors 2 and 3 of their building and made it into floor 2 for ours. And then on the third floor, we took 4 and 5 of theirs and put it onto one floor. We have growing on the east and west sides of the building with all their central offices right on the top floor. And so these are just north-south elevations of the building. The south is all growing and exposed to the street, and the north has all the private, smaller spaces. And then in east-west, it still maintains a step up. In their original design, they had 20-foot greenhouse spaces, and we maintain that throughout this design also. And then for the exterior, we wanted something that was like they are now. They're full of life, and took their idea of what they had in all their painted lockers and tried to apply it to the exterior of the building. And so we have metal panels because they're durable, they're well insulated, and they're local. They're local enough where we can use them for Living Building Challenge to meet within our distance requirements. And then polycarbonate panels for the greenhouses. They're typical greenhouse construction. They're lightweight, and they are one of the least expensive per R value you can get for thermal efficiency. And so this is a typical interior perspective of the greenhouse. And then our gathering space on the west side.
So actually, do we want to pause a little bit? I don't know if there are any questions or points of clarification that need to be made. Go ahead.
Question. My first question is, what is chicken heat?
Okay, so we'll get into it a little bit more in the presentation, but they have a lot of composting on site. And so they use the chickens inside the hoop houses, and the composting, the manure from the chickens generates lots of heat. So they're able to utilize the heat already from the hoop house, the heat from the compost, from the chicken, also from the chickens, and then they can grow in that area as well. So we had on there the winter spinach with the chicken heat, so they grow winter spinach inside the hoop houses with the chickens from all of this heat generated.
Thank you. One more question for you, especially.
Uh-oh.
I was watching your body language when you were talking about your visit there.
Yeah.
You completely changed. See, I'm a person that believes that the architects need to be out and away from the desk. You need to be out there to see, feel, touch, so you can understand exactly what you're dealing with. And you should have saw yourself how you just came to life, describing how you enjoyed.
I thought you were going to say I did the opposite.
No, how you enjoyed that visit.
I did. It was a very, very good experience.
We were discussing that we feel you need to get out of the classroom and get out there and touch and feel so you can integrate all the aspects of what you're going to be working with. So that was good.
Thank you.
One comment. I thought, wasn't there a code issue with the 5-story that going to 3 improved? You're going to get to that. Okay. Because maybe a preface to why you're deviating, just a sentence or two about why you've embarked on changing the whole thing before you go into showing it.
Sure.
Can you, maybe I missed it. What was the business reason for this building? Is it education, or is it growing and doing what they've been doing, which is basically serving the community?
It's both.
Well, I guess part of the message is you need to make sure that what the business reason for them today is not impacted.
Okay.
Somehow you've got to basically show that, again, they're there for a reason to make some money, to pay for their being, their well-being. And is that going to be, that whole reason for being, going to be changed as a result of being a multi-use facility? Have you provided them with that same amount of income or more? It didn't really come across in the programming.
When it comes to the programming, they mostly see this new building as an addition to what they have, so they want to continue with the growing in the market so they can sell. And then also incorporate actual classroom spaces into the building itself. Currently what they do is that when they have classes, they just do it on site in the individual greenhouses, but they wanted to have more of a learning atmosphere indoors. So the education part of it is supposed to be cohesive with the original growing institution ideas.
Which I
Maybe
think
you can change the question a little bit. Okay, there's a business performer for this. Who's going to pay for this? Who's going to pay for the rent?
That's a good question, and we actually had that conversation early in the semester, thinking, why do they need a large building like this? But we also are working within the competition guidelines, and
Understood.
yeah.
But that is going to be in the background of any business decision to do something. And I think through this whole effort, you need to be thinking that through, similar to last year's.
Yeah.
I guess to follow up on that as well is how do the changes you made in the architecture help them achieve their mission or some of the things that they're trying to get out of it? Is there advantages to the design that you guys came up with to the community spaces, for example?
Yes, so that was a big thing that we wanted to stick, like before they would have classrooms that were all the way on the north side of the site and they had no connection to any of the greenhouses. So with our redesign, while there may be a corridor or transition space in between them, it's a direct line of sight and they can be in the classroom but actually see into the growing areas at all times. And so that was a big part in how we reorganized the building, and so that everything had a connection to those greenhouses and you always felt like you were in there but you weren't in there at the same time. Did that answer your question?
Go ahead.
I noticed you had a lot of windows there, and in one of the pictures it looked like there was quite a bit of glare coming in the windows on the people and perhaps the computer screens, etc., inside the room. How are you looking to overcome that glare?
Well, I can honestly say we haven't really gotten into that as much. I think was that on the gathering space perspective. Yeah. So that's all.
It was one of your early slides.
It's all greenhouse on that one side of the gathering space. So we would have to, I guess, treat the window partition that's between them in order to reduce that glare.
You might look at window film, you might look at a few other things like that, or even frit on the top part of the windows. But the other thing I noticed, there were a couple of fish tanks there. And you talked about worm compost. Have you looked at using the waste from the fish as additional compost?
The guidelines in the competition, yes, but the guidelines in the competition were, not to use a pun, were really kind of fishy when it came to what you should do and what they suggest that you do. So the fish tanks that they had at Growing Power were very prevalent. They used them in every greenhouse almost, and then the ones that they had in the base building that they gave us were only for demonstration in the marketplace. And so the way that we took that was and we'll get into it later, but our water system that we've implemented in the building supports their existing fish growing area significantly. And then we have also allotted for space in the marketplace, which we haven't really specified where yet, but in the marketplace as to where those demonstration components will go for the fish. So it's different than what they have now pertaining to the fish.
So what do they actually use the fish for now?
Well, it's aquaponic.
Yeah, they use it, well, we had a slide of it, but they have these stacked configurations on the bottom. They're 4 feet deep into the ground, and so there's fish, or water and fish inside these 4 foot deep trenches, and they go the entire length of a greenhouse in some of them. And then there's a wood construction that there's a level like waist height of all aquaponic growing area, and then there's another level, another 4 feet above that of all aquaponic growing area, and they cycle the water from the fish into the plants. So it's a closed loop system, very simple, PVC piping, looks like, you know, some guy went in there and, you know, makeshifted himself. It's a really simple, very effective system.
So are they therefore using some of the waste from the fish in the growing?
Yes.
Okay, that's what I thought you were saying.
Yeah.
I wasn't sure.
Yeah.
Okay.
I just same comment about the light and glare, but I was thinking heat gain as well. And I think you'll probably get into what you're doing with your structure in that area. So of course you need that for the growing portion, but how do you balance that, especially with a space where you're going to have a lot of people in the heat gain? And then you had mentioned something about how part of the parameters asked for this building to be able to be relocated in a different location. And I was wondering how, when you were showing where the materials are going to be coming from, you know, how do you account for that? So did you specifically choose your materials to be something that would be prevalent or available in any other location?
Yeah, we're actually going to get a little bit into that. We looked at all the sites that we could possibly move to, and we looked at the most used, like the commonly used materials, and the commonly, what's the word I'm looking for? like the actual subs, the people that actually build everything, we look for the most disciplines that actually have that. Like the steel, there's a lot of steel workers everywhere that can build in different locations, concrete as well, and then we looked more for timbers in areas north, obviously with the most amount of forests and environments that actually suit that. So.
Other questions or comments? Okay.
So let's start with the structural. We will go over some of our goals, and then we will present three different variations that we did as a preliminary structure. Then we will go over our decision process and how we decided to pick the structure or the material used for the structure, and we'll show some design development for the structure that we decided to go with.
Relating this back to the Living Building Challenge, or LBC, I'll probably name as that. We're obviously mainly related to the materials pedal, as we can't be on the red list, which is a list of actual materials that are banned by this program. So we made sure that all of our structure was completely free of any chemicals or compounds that are banned by this list. We also were looking at locally sourced materials and people who can build our structure. So the contractors. And we're also thinking naturally, as structural is naturally looking towards construction. We're looking at the waste, and as we build, we make sure that if there is any waste, that we reuse it in areas that we can. And then also another pedal that we relate to is beauty aspect, as we want to make sure that our structure is pleasant and we want people to be invited by it.
For the structural team, our main goal was to design a modular structure that can be easily and efficiently, with minor modification, changed and adapted in different locations all over the United States, while keeping in mind the availability of the materials and then the density of the site. So we tried to design a structure that can be easily modified for that, and we also tried to design a structure in a way so that it's highly integrated with all the other mechanical systems, and we also looked at the different, you just mentioned, the different materials that we used, or that we studied, and that could be adapted in different locations.
So our three main materials that we focused in on in our studies and our research were concrete, wood, and steel. Precast concrete, to be more exact, because of the constructability aspect and modular thinking of our structure. So this is the 500-kilometer radius from Milwaukee, and the regions in brown are the iron ore deposits for steel manufacturing, and there's a steel manufacturer that we took a closer look at in Waterloo, Indiana. And then the green region is the foresting regions in Wisconsin that the state of Wisconsin allows you to sustainably harvest trees from. And then a main glulam manufacturer is in Peshtigo, which is in northern Wisconsin here, close to the UP. And then there's cement deposit areas all in Ohio, Indiana, Illinois, and the main manufacturing facility that we took a look at there was in LaSalle, Illinois.
The first design type, or the first structure, was a precast concrete structure, and the main advantage of this of the concrete structure is that it is it's easily or it can be integrated with the mechanical systems easily. It creates these big shafts that could be used for the mechanical systems under the floors. It also has a very good fire resistance. It's naturally, it doesn't combust. But some of the main disadvantages against the concrete structure is that we went with a 70-foot span for our main bays here, and that was inspired by the greenhouses. The greenhouses are generally 70 foot by 20, so this is what we went with. And for that reason, spanning that 70 feet was high. It's hard to achieve with the precast, or usually for parking structures, the design loads are 40 PSF only. So, but for our building, we were going with 100 PSF live. So that was hard to do. Also, the connections for between the elements and between the members in a precast, they could get very hard to design and construct, especially in areas where for high seismic and wind. And we had to consider that the structure had to go in Miami also. So that was one of the bigger disadvantages for the concrete.
The second structure we took a look at was wood construction and heavy timbers, utilizing the king post system. And so some of the advantages for this king post system were that many of the resources are in Wisconsin itself, and the main manufacturers, again, from Wisconsin. And there's a greater appeal with a wood construction building that's fully exposed structurally versus a concrete structure that they use for the baseline. It's also lightweight compared to a concrete structure, which will minimize our foundations. But some of the disadvantages, as you can see up here, is that with the king post system, you want to get as much vertical distance for this king post to resist that moment on the glue lam as possible. So head height was a main disadvantage, as well as this system is a very custom system. Therefore, pricing could be a little more expensive than a precast concrete or a prefabricated steel system.
The next structure that we looked at was steel, specifically rigid frames. Their modularity is a big factor in the ease of repetition of the structure. It's also obviously very, it does a great job at spanning large distances with its high strength compared to little material required. However, it isn't very passively fire protective, as well as it's not as nice to look at as like wood would be. So, kind of phasing out fire protection with our structure change, or from 5 to 3 level change. Originally, the project said that our building was Class F, or Group F classification, which they classified the greenhouses as F, but it actually in the code says that it is Class U, which is a much less fire protection code. So, relooking at all the spaces, we determined that we're actually type A3 classification, which we can then drop down to type 2A system, which with our 3 levels and our 15,500, we're being under 15,500 per floor. We actually don't require any fire protection as long as we have a sprinkled building. But we also realize that with the type 2, we cannot have combustible material, and in order to offset the, well, actually I have to get into that later. We were looking at using wood as one of our floor structures to kind of give a more natural look to our building. So we couldn't use that flooring if we used type 2. So we dropped our type down to type 3B, and by doing this, obviously we can't do it based off the 2 levels or 2 floors and 9,500 square feet per floor. But in the code, we'll go back. In the code, however, if we have an automatic sprinkler system, we can increase our floor by 1 to make it 3. And we can also increase our building based off of our frontage of our street. We increase that obviously with making our bays 3 bays instead of 1 on the street. We can increase it to 29,000 feet, or 29,000 square feet per floor, which is enough for our 18,000. Our max floor square footage is 18,000, so it obviously is able to take care of that. So by changing our type to type 3B, we don't require any fire protection except for our exterior load-bearing walls, which require 2-hour fire rating, and this is also with the exception of our sprinkled building. So looking at the separations between spaces, we only require 1-hour fire rating for the enclosures that separate type A, which is our assembly space, from our parking space, which is obviously, as you can see from the architecture plans, the parking is below the large assembly space, so we'll need a 1-hour fire rating there. We also have between the offices and the greenhouses on the roof, or on the 3rd floor, we'll need a 1-hour fire rating between those spaces as well.
So our overall decision, comparing the 3 modules that we were studying, we took a look at the different grading criteria based off of the Living Building Challenge, as well as constructability. Some of the main focuses that we decided to take a look at were its life cycle assessment between the materials, and we actually found a study that showed that initially wood has a better carbon footprint compared to concrete or steel, but over 100 years that separation becomes almost negligible, and that's what we were designing for, is a 100-year building. Also, the volume of material required to have our 70-foot spans was a little bit of a challenge for concrete and wood. So therefore, I didn't talk about this grading scale. The grading scale that I have here, 1, 2, 3, 1 being the worst, 3 being the best at responding to these different grading criteria that we had. And also, because of the volume of material required, is our the impact on foundations. Because we have very poor soil on the site, we needed to consider foundations substantially. Therefore, the concrete design was the worst, and steel was actually a little bit better because of the amount of material that we would need for wood to span that 70 feet. And also, after completing this top matrix, we also had a team discussion for an integration aspect of how they thought their systems would integrate within our building and how our building would integrate with their systems. We unanimously decided that the steel option was the best option for us because of its ability to respond in a biological sense, having the tapered profile that addresses the forces the best compared to the concrete and steel. After that, we took a look at the architectural plans that we had, and we did a live load assessment. And because we have so many different types of assembly spaces, it ranged from 70 PSF in toilet rooms up to 125 PSF in our storage rooms. After consideration of dead load as well, the maximum load combination that we had was the 1.6 live times 1.2 dead, or plus 1.2 dead, to 276 PSF that we designed for as a maximum load on our structure, so that we can have this modular aspect of you can take our module and move it anywhere in the building and it would still be able to work as we want it.
The wind loads are also another aspect that we have to understand. So in order for us to understand how the building would respond to wind loads and how the wind loads affect the building, we did a wind tunnel simulation in RoboStructural, and we took we did the study for the wind coming from all different sides to the building, and that helped us generate maps that showed the pressure on the enclosure and the wind velocity and everything, all the forces on our structure. And we used that for 115 miles per hour for our current location. And then we did another analysis for Miami to also see how the design would get affected because of the wind loads.
So overall, this is our structure that we actually designed for. We're going to break it down now for you. So this is our floor structure, our tapered members of our rigid frame, all aligned to direct the forces down to the foundations as it moves down. So the actual floor structure itself begins with the rigid frame, and then on top of that will be the W12 by 14 wide flange beams, spaced at 5 foot on center, with a nailer plate on top so that the ease of connection between our wood structural decking. Like I said, we wanted to integrate some of the beauty aspect into our structure to give it more of a lively look from underneath and above. So that's a 3-inch wood structural decking on top, connected with nails to the nailer, and then the nailers bolted to the wide flange. There are special cases where we actually had to frame around the elevator shaft especially. We couldn't bear any load on that structure, so we had to have atypical connections as it connects from web to web in order to take on that floor load where that meets the elevator shaft.
Our greenhouses also use the tapered frame with smaller sections, and the roof is has a double pitch. The first slope is a 1/12 slope from the primary frame, and then we used scissor trusses on top of that for a 6/12 pitch. That was the best pitch for the integration with the electrical, and also this is a fairly used slope for scissor trusses. They're mostly used as 6/12.
In our envelope structure, the team decided to go with metal insulated panels exterior envelope that needed to be 6 inches thick to accommodate that 2-hour fire rating using mineral wool insulation. And we looked at common applications and how they're connected back to the primary structures. So one of the most common is actually utilizing a Z-channel for vertical members as well as horizontal members that would be able to support these panels that are oriented vertically all along the building in 30-inch modules. So they're spaced, the vertical members here are spaced 10 feet on center, and then the horizontal members are spaced 5 feet on center to better incorporate within our structure and give a more modular aspect, because we have a 15-foot floor to floor in all of our spaces.
In a rigid frame, obviously an important factor, a very important factor is the connection design itself. So for the different members, we tried to keep the connections as simple as possible, and we used bolted connections throughout for every member. We used the bolts instead of welding because it's cheaper and it's easier to be done on site, and it's a lot faster to construct. And through the design, we tried to minimize the use of materials. And for example, this is one of the sections that we are still trying to work on to add more stiffeners to the connection in order for us to be able to use even smaller members.
A positive for a rigid frame is its ability to resist lateral forces in the east-west direction, but it also has to have some bracing for the north-south direction for any wind loading. So a typical bracing for a rigid frame is normally a rod connection with X bracing from corner to corner, which we use for for the exterior. But on the interior, for ease of passage between spaces, we move the connections up and actually utilize chevron bracing, as you can see up in the corner, and then a high X up in the greenhouses. There's no connection at the top to make that chevron easier to connect there. So it's a different connection up there as well. The chevron bracing, however, it does integrate with our rigid frame, as it does make a mini rigid frame as well with that connection.
In a foundation analysis, we found that we needed to use spread footings for our main foundations, and we needed to maintain a 4-foot distance between the grade and the top of the footing for frost line depth. And because we have 2 spaces here that are only slab on grade, we only require a grade beam on the perimeter of the slab on grade. However, at the bottom of each column, there's going to be another concrete column that leads to a concrete spread footing to distribute that load. Another thing that we had to really consider with foundations is the water table. In our geotechnical report, there's a paraphrase in there that says that after you dig 12 feet deep, the water raises 5 feet every 5 hours, so 1 foot every hour. So we had to waterproof all of our foundations below grade, as well as insulate all of our slabs from grade to 4 feet below grade where the frost depth
For
is.
the basement area, also for that floor, we had to after sealing around the basement, we have to design connections to actually hold down the floor so that the static pressure of the water pushing it back up, it doesn't crack the concrete. So we have to use a heavier slab in there.
Touching on the construction aspects, as you can see, the green is all the excavating zones that will need kind of integrating with the mechanical and their systems. As you'll see further on, they're going to be using geothermal loop. So that'll be running everywhere. So that's the necessary zone that needs to be excavated up top. Our materials for before construction, the unloading will be moved to the back, off away, out of the way, so that we can place cranes here and here to move that material across to build our structure. This is just showing that we're gonna start from the back and move our way forward to as our construction, as we make our way down. These greenhouses are going to be staying, so we can't touch those. We are also thinking about using, there's an existing house that Growing Power actually owns that we're going to look into using instead of bringing in a trailer, just reusing what's already there for a meeting space and for gathering for the construction workers. We're also looking at using that property as parking for them as well.
Moving forward, some of the things that we need to consider are lateral drift, especially in our alternate location, Miami, as well as the uplift due to water on the foundations that Hyan touched earlier. We need to further analyze that to figure out exactly how robust our foundations need to be. Our construction needs to be worked out with a little bit more with phasing, scheduling, and logistics. And vibration for the floors and serviceability loading. We need to consider that as well moving forward in our floor design.
Questions? I'm sure there's a lot of them.
So why did you pick the rigid frame? And why did you
It's
form it the way you did?
so what was it,
Biomimicry.
Yeah, biomimicry.
So what nature does naturally is where there's the most force, it becomes thicker and stronger. And with the rigid frame, we have a pin connection in the middle. Therefore, our moments are less in the middle and more towards the ends. So the rigid frame actually, for lack of a better term, mimics that moment, and it's smaller towards the middle and it gets thicker and more tapered towards the ends, where it takes on the most loading and it could be passed to get to the foundation.
Just like a branch coming out of a tree comes out big and then it gets small. But another important aspect for us to pick this is the actual span, 7-foot span. With the concrete, it was, as we mentioned, it was just very hard to do. And the steel is also available throughout the United States that can be easily. It's not hard to get, and there's construction is also fast with that.
Put that story in your presentation.
Right, because one of the questions I was going to ask, in the materials, you had biomimicry, you had timber as 2, steel as 3, and precast as 1, and it was like, how can steel be number 3 in biomimicry? I would think timber would be number 3, but you just explained it. It does need to be explained when you show that, because people are going to wonder about. You don't want them wondering about something that they're not asking a question about, and you don't get to it till the very end. So that would be a good time to explain that.
Struck me as well, same thing.
When you put bents on top of bents, if you look at an upper level, the outward force at the base of that bent, is that withstood by the pin of the bent below?
Yeah, it depends on the pin and where the location of the bolts as well.
So that the outward kick
Yes.
has to be handled by intention by the member below.
Yeah.
Okay.
Were you intending to use a pre-engineered building system for this?
It goes back to like the modularity, the ease of construction as well.
The reason I asked the question is it probably would be a good idea for you to contact a butler or Barco Pruden if you're planning on doing that. Because every one of these that I'm involved with is basically a tie rod at the base, from foundation to foundation across, to tie it from kicking out. You'll find that if you run through Barco Pruden command, BP command, you'll find some incredible forces for a 70-foot span out that you need to tie back in. So that's point one. And point two is, again, when you start stacking these, you have to take that into account and in your design of that floor structure. Because I didn't see any sections there that basically supported that. And number three is you've got some pretty good areas for snow loading. Have you taken that into account?
Yep, we still need to look into that design because the areas that where the snow load can accumulate, we're using those also to channel water down. So that area is we have channels that hang with bars from the structure. So that part is still not designed. We're still
With all the heat that you're going to be losing out of a greenhouse system, you're going to have ice dams going forward. Just for points that you need to take into account.
Is there a reason why the roof is double pitched?
To naturally force the water into areas, like there's actual kind of like gutter system in between in that 5-foot bay between our greenhouses where they meet. It's then funneled down into a collection area, which is then reused in our building as well.
So is there, if you have the bay, is there collection areas at the short sides?
It'll be a gutter system there.
And that's taken into the center?
Yes.
On one of the slides, you had that structural steel was athletically appealing. I think you meant aesthetically appealing. You might want to change that one before you make the presentation to the judges.
It is athletically appealing.
Also, that is true. That is true, Ralph.
I'm pretty bad at spelling.
Matt?
So you talked about sustainably harvested trees in northern Wisconsin. So describe what a sustainably harvested tree is, and then
From my research, one of the main methods that they use when sustainably harvesting trees is that they take a plot of land and they section it off and only cut down the mature trees, leaving the saplings and maybe a few premature trees that are a little bit taller that can shade and shelter the smaller saplings, and then allow those to grow back, as well as they plant 125% of what they take out.
what's the standard under living building challenge?
Well, it was whatever you take away from the environment, you have to put back in as well.
And they also the harvesting company needed to be declared, as well as they also needed to be licensed in a special way that allowed them to harvest trees for a living building challenge building itself.
Forest Stewardship Council, maybe?
Yes.
And what about the ash trees?
We took a look at ash trees in a little more focused look because of the ash borer problem that we're having in Michigan, as well as getting into Wisconsin, where they have to cut down these trees, but they're perfectly good for structural usage. Therefore, some of our flooring is going to be used as was intentionally we want it to be used as ash wood versus Douglas fir, oak, or other tree types that are not endangered from the ash borer itself.
You said that you have to take some of the construction waste and put it back into the building or minimize it in some way. How are you doing that exactly? Have you thought about that?
With this pre-engineered system, we won't have much waste, but the site itself right now has a large collection space for like wood that is brought in from the community and recycled. There's a recycling area and whatnot. So we're going to look in. We're actually wanting to use reclaimed wood as all of our flooring. So that'll be on top of that structural wood decking, which can also integrate back into our ash, reusing any of those trees if we obviously run out of all of our reclaimed wood that is brought to our site.
Also for the waste from the construction, it's not some of it, it's actually all the waste has to be treated, so you have to have separate trucks on site, always available during construction, and then there's someone responsible. Their only job is to make sure that everything is recycled properly.
I know this is only at a SD phase level of design, but have you guys given any thought to the integration the structural system with mechanical and electrical system?
With those wide flange beams, we're actually able to run electrical and mechanical north and south. We also have large shafts, 4 shafts in the middle of our building, so they're, everything's able to run. Let me go back. Keep going. Go back to like my structure.
See it clearly.
You can keep going back. One more. One more. Sorry. You can see these shafts here. There's 4 of them. There's 2 located where the 4s meet and where the 4 connections meet there as well, to move everything vertically. And then the wide flanges are able to move north-south as well as east-west in between these 5-foot spacings. So it's kind of able to channel any way we need.
Another point of integration is in our greenhouse roofs, where the mechanical team, they'll talk about it later, but they require natural ventilation, where we're going to have operable windows on our ridges, as well as the electrical team is going to have PV panels on the top of the ridge, just on the other side of the operable windows. So that's another point of integration, as well as the water channeling organization that we have that we're going to be integrating within our structural system throughout.
And I mean, I agree with Tim. The things you guys just said, I think you should say in the presentation. Last year's team did an excellent job on how they integrated back and forth. I think you should say things like that, why you did that and how it helps the other disciplines.
I know that they actually get into it a little bit deeper in the engineering.
And one of the things that we had trouble with was, where do we stop and where do they pick up?
Yeah.
So a little
These
more
are
oral.
good comments for us.
We try to be integrated. I
Yeah.
think you said electrical once and you said mechanical once. So you might want to just say those terms a little more during the presentation.
And just on that, like if you guys repeat information, your audience, this is the first time they're hearing it, it may seem redundant to you, but it's not going to seem redundant to us if we hear it twice in like an hour presentation. So the more like kind of you can set them up for explaining their system, I think the better it will be for them to like explain it and have us understand it even more when they come down with their more detailed information.
Especially the shaft areas, because it wasn't really covered in the architecture, so naturally it would probably be covered more by you guys, because that is, you know, you're doing these modular systems, and we didn't really hear about, you know, we didn't see one module. We've seen it as a whole, but what does one module look like, and why, what spacing is it, why is it put together the way it is?
Another big thing I guess I didn't hear, because you were targeting net zero, net positive energy. How does the massing and the bridging affect the thermal performance of the building?
We are using the for the enclosure the insulated steel panels, and those connect to the outside exterior of the building. And the way the connections between the girts and the actual panels, the way it's done, it's thermally broken. So for our enclosure, there's very little thermal bridging for the lower floors, and for the greenhouses, we're not so much worried. The mechanical team will get into that more, but they're not so much worried about heating or cooling these spaces for the greenhouses. So we're not using insulated panels in the greenhouses, but for the other floors, it's the structure or the enclosure is thermally broken from the actual structure. So that also reduces the energy use in the building.
I liked when you said that you were designing for a 100-year building. I would have liked to have heard that earlier on, because then that gave you a better framework. I got a little more confused when you were explaining about designing for the fire protection. I understand your decision-making process, but by going through the decision-making process, it made me feel kind of like you were designing to get by with the bare minimum, instead of saying, you know what, we designed it this way, utilizing the steel, and it met the requirements that were necessary, and then just leave it at that, instead of just going down and down and down and then saying, well, is it safe, you know? What about the wood roof, and, you know, all those people gathering, and, you know, then people start ruminating, you know, instead of just saying, you know, it met all the requirements, and still when we were able to expand the square footage, and then it solved all our problems. Just turn it around, make it positive, and shorten that part up.
And if you can say, in any design over 3 stories requires fire protection, if you're confident of that, that's a huge reason for what you have, and it throws into question designs that aren't, if they aren't.
You guys also talked a lot about how you were looking at 70-foot spans, but I think when you described the architecture, you didn't explain where the 70-foot spans came from. Were those in the original building?
Those were inspired from first the architecture was inspired by the Louis Kahn building. That building itself was inspired by barns that they were used for cattle, and then they were roughly that size. So our inspiration for the architectural comes also from a farming environment, and then for the new design, it's also inspired by the actual greenhouses. And the actual greenhouses are around 70 feet long. So that was kind of, this is why we went with this span, and we wanted to maintain that shape.
Does that provide any practical benefits for the owners?
They wanted a lot of frontage and access to the street, so by elongating that,
With the 70 feet in particular, is that because it's that they can use the same size boxes or something? Is there some sort of benefit they're getting by getting those the same shape and size of the greenhouses?
There's benefit to the internal space.
Yeah.
It's the internal space is more open. If you look at the base building, they had 20 feet spans, and then they had a lot of columns in the building. So by doing this, we minimized the number of columns, and then we also gave more open spaces, so there's more flexibility on the inside. You can put walls wherever you want. You can modify the internal architecture if you want. Also, for our gathering space, we wanted to keep that help keeping that area, that span, help keeping that area open. In the baseline building, there was 2 or 3 columns right in the middle of the gathering space, and then we thought that's not necessarily the best way to go. So that also solved that problem for us.
I think telling that story would be good. Because I think even in the first presentation, you guys had an image that showed some sight lines and where the columns were and how that would affect it. So explaining why you went to a 70-foot span to minimize that impact would be really good.
And then overlaying one of the images of the greenhouses to show how open those greenhouses are, because that's an image they're familiar with.
And as people are asking questions, you guys seem to have the answers of why you did things, but they're not necessarily going to be able to ask you that many questions, and so you have to tell that to us beforehand. Why did you choose those systems? Convince us.
Mina, you have a question too?
Yeah, I'm looking at this structure here, and usually when you have your foundation on 2 levels, you end up with a problem with the settlement because you are dealing with 2 types of soils, or at least 2 soils with 2 different properties and different settlement. And in this case, you are most likely end up with some kind of differential settlement between the foundation in the middle and the foundation on the side. It's a good thing you have a 3-hinged frame. This can absorb some of the differential settlement between these 2 foundations, but you need to highlight this one. You pick the 3-hinged frame to handle the differential settlement. The other thing is that your floor for the basement or for the lower level, how much water head are you planning to resist?
The water?
Water head on
about
5 feet of water head.
Also in the geotechnical report that was given to us for the site, they do recommend the use of these spread footings, but also because of the poor soil conditions, we have to excavate and use engineered fill. So that helps in the for the settlement problem. Because the site, we have to actually dig the site and fix the soil and use engineered fill under it.
What is your question about the water, or the concern for the waterhead?
Well, I'm trying to think over this span. If you have this much of waterhead, 5 feet of waterhead, you need the thickness of the slab, the weight of the slab you are adding to resist the waterhead. So, because the density of the concrete is 2.5 times the density of the water, so if you have like 2.5 feet of waterhead, you can have 1 foot slab, and it will resist the waterhead. It doesn't have to be reinforced. Because if you don't have columns in the middle, then your slab is supported at its end, so it's very simply supported over this span, which is how long? 70 feet. Well, how you gonna resist the waterhead over water pressure over this much of a span?
Yeah, this was one of the things
Yeah.
that we have to still design.
So you basically check how much water exactly you have, and then try to depend on the self weight of the concrete to just resist this one. Then it doesn't have to be reinforced at all.
The evaluation matrix that you put up, was there a reason why you didn't evaluate cost of the 3 different systems?
We initially had cost as one of the evaluations criteria. However, we found it difficult to provide cost for a glulam timber construction, how it was king post and so very custom. Therefore, if we had better numbers for 2 but not for the third one, we felt that it wouldn't be a true comparison. It would be a little more difficult.
Maybe an interesting way, if you could find a creative way of doing it, I don't think you can lose cost in any of these valuations. You may have to think that thing through, how you want to present it, but it needs to be part of any presentation.
I have a real basic question. How much time do you have for this total presentation?
Yeah. Well, it depends on whether we're finalists or not. I mean, tonight's presentation is quite long because we need as much feedback.
Right.
And I think we have, well, if we submit to all 5 categories and we're selected, I think, what do we have, 75 minutes total?
So for all 5 categories?
Yeah. Well, we can just present it as one project and touch on all 5 conditions in 5 categories. But yeah, 75 minutes total would be. What did you guys have last year?
45.
So maybe it's not even 75, so it'd be more like,
You don't get an extra 15.
okay, so we presented 45, so it'd probably be like, what, 55? Okay, 55.
Yeah.
Anyway.
So it has to be concise, and look up the word lucid, and try to take extra words out. Tape yourself, listen to it, and try to say, I could say that in 2 sentences, and rather than stumble over an introduction, just go right into the point, and listen to yourselves and try to get it down to half the time.
Talk about it to the group in the same passion that y'all do when you're in the studio, because when you're in the studio, you guys are just jazzed. You're talking to each other like you're friends, you're excited about it, you're passionate about Living Building Challenge, and you talk to the group and you'll kick some ass. And I've heard like 4 different people talk about, tell that story, and that's exactly what this is. This is a story.
I think, so far, I think both groups, I think, were excellent. I think your slides are outstanding with what you're presenting. Just a couple of my comments on them. In my opinion, I thought the text was a little small on there. And I don't know how you see it in the back. I don't know how far away.
Bigger from back here.
Pardon? Just my opinion, I thought it was a little small. Bullets, I thought your bullets, you should have a space between. You have a bullet, then you have what you're saying. You might want to have a space or 2 in there. And then sometimes you had a bullet, then another bullet, and I thought it was a subheading, and I wasn't sure if they were supposed to be lined up or not. your table, Tom, on where the products were available was hard to read at the bottom. And I would even put, you know, growing power, put their logo or something and put it up there and point it to the site so they see, you know, that's what you're talking about. And then the overall decision, the last column on the left, the bottom, all the text was all over to the right. So that should be centered. And in the first group, when everybody's standing up, everybody's standing the same. You know, some had their arms behind them, in front of them, some had them folded, some had them in the pocket. I think everybody should stand mostly the same way. And then a couple on the first slides, put a north arrow on some of them. I know some of the floor plans did, but the site plan didn't have a north arrow. It'd be nice to get that on some of those.
Anything else for the structural group? Otherwise,
I think the slides are outstanding.
Yeah, very, very good.
Just one other quick question. The funky angles of the solar array, what's up with that?
Electrical team's coming up next.
Okay. You know who designed that.
Just before you guys leave, you also, for the lower frame, you need some sort of tie to take the horizontal force at the foundation level.
All right, good job. We ready for the electrical?
Yep.
Hey.
So we are the electrical team, and kind of going back to the Living Building Challenge and trying to look at this aspect of biomimicry. You know, every one of our systems, we're trying to look at it as a different part of a biological system, I guess. And with electrical, you know, it kind of ties back to a nervous system, and something that, you know, came to mind for me was that, you know, we all have nervous systems. They're working, hopefully, if you're healthy, but they're always in the background, and you don't really notice them. And that's kind of what we're trying to do with our electrical system, is just kind of be there, support everything else. And like Steve said earlier in the presentation, you know, simple, but not simplistic. So that's kind of what we're doing. As an overview, some of the things, the standards and the philosophies that guided us, Living Building Challenge, of course. We're going to look at some of our design goals, how we went about selecting the alternative energies that we decided to go with, how much energy the building is using, what the design says it went through iteration, power distribution, looking briefly at special systems, and some lighting control strategies. The whole idea is to be as efficient as possible and try to optimize the system.
So for the Living Building Challenge, the pedal that mostly affects electrical would be the energy pedal. And one of the criteria that we need to meet for that is to have 105% energy production on site. So in order for us to do that, in order to integrate with the other systems, we had to do a couple of optimization measures. So lighting was a big deal, controlling it and getting the right type of light fixtures in the space. So we would not only just have good light, we would have good efficiency for the lights. Plug load, we would put them on schedules, and that would help reduce our overall energy loads for the building. Allowing day lighting for most of the spaces helped reduce the lighting load. And then also was having an efficient HVAC design. We can limit our energy that we need for that. So for us to design for the AEI competition, we needed to be able to address the building power distribution. For the Living Building Challenge, they require some type of battery storage. Lighting design, fire alarm, infrastructure, and security are all stuff that we also had to look at for the AEI competition. We need to look at them when we're talking about innovation and with life cycle cost analysis, so we can think about it as a holistic approach. And then all of our disciplines should be working together, so that's what we're designing with. So the baseline building that we had originally showed, the 5-story building, with all the square footage in the spaces using a typical ASHRAE watts per square foot, lighting power density, and typical numbers used from RS means values for the different type of spaces that we had, which were manufacturing spaces, we had office spaces, we had classroom spaces, and we came up with a devices level HVAC and miscellaneous watts per square foot, and then using that we made a calculated connected load of 388 kilowatts that would be needed for the system, and a demand load when all the demand factors were applied of 286 kilowatts. So the power density for this typical building would be 7.61 watts per square foot, which when most people are designing for a building, they're usually going with about 10 watts per square foot, and this baseline building is already underneath that. So just as an overview.
So going to looking at some of the sustainable energy strategies that we looked at. Obviously the five, wind power, solar, geothermal, hydroelectric, electrical generation, biomass, and the fuel cells. Some of the influences to the decision were if it was consistent with Going Power, Living Building Challenge, if it was in line with their criteria, and then also what was available on the site that the project is located at. So for Growing Power, they're very much about using living systems and sustainability. So basically every strategy that is available, they would be open to using. When we got to Living Building Challenge, we were a little bit more limited as far as our selections. Living Building Challenge requires no combustion on site unless for emergency uses. So the biomass, using the methane that's produced on site was not allowed, and then also the hydrogen fuel cells, because one of the off gases of hydrogen fuel cells was CO2. Something we found that was interesting was with the biomass that produces methane. We found out that actually using the methane as a fuel and having a CO2 off gas afterwards is actually less detrimental to the environment than the actual methane itself. But still, to be in line with the Living Building Challenge, we decided not to go with that. As far as the site limitations, we looked at some of the wind velocities. We did a disarmament study, which I'll talk about in a minute. We look at some of the constraints because we were close to a residential area, so that limited us a little bit. As far as solar, they do have an existing solar array on site, so that is something that we can use. And then as far as the geothermal power, for electricity generation, it's regionally unavailable there in Milwaukee, Wisconsin. So that struck that out. And then the hydroelectric energy. We did look at using rainwater to power a hydroelectric turbine. And because we didn't have enough head with a smaller building, we didn't have enough pressure to actually generate any useful electricity. So we decided to go with the wind and the solar. So in our wind evaluation, we basically looked at every direction that the wind comes from in our location, and what we found is that it varies throughout the seasons. And basically what this table shows you is that certain percentages of the wind from this particular direction. So we're looking at the summer, winter, spring, fall seasons, and you can see these darker green areas. That's where it has a higher percentage of wind coming from that direction, and this is the velocity that it comes in. So those were the two driving decisions for the type of wind generation we can use. And then as far as the size and the aesthetics of the actual wind turbine, that was going to be a factor as well in the decision. So we looked at one possible option, which was really interesting. We found this and thought, because of the multi-directional use of the wind to generate or to turn the turbines for electrical generation, this could have been a viable option. We actually got pretty good electrical power out of it for our site. It works well with lower velocities. But one of the cons was that it's actually 80 feet by 50 feet at the base, and it's 170 feet tall, which our building is under 60 feet, so it's a little bit, it's basically taken over the site with that. So we kind of did a model to kind of see how it would fit on the site, and you can see it's a little, the neighborhood is actually back here on the other side of the creek, so we're casting shadows, and it's just kind of an eyesore. So we kind of looked at some different options from there. So we looked at the vertical axis wind turbine as well, and this also had a low cut-in speed. And it really just the look of it, you see smaller windmills at farms all the time. So this was kind of consistent with that idea, and was able to generate a little bit of power for us, which we'll talk about in a little bit. If it's grid tied, it's saying it's 530 volts DC per turbine. So this was one of the options that we actually decided to go with to help supplement the electrical power. And here you can see them on site. So we basically planted them on the east property line, and they don't overpower the site, but it also acts as a teaching tool for the community aspect of growing power to help people see, what nature can do to help out in just, sustainable building systems.
So also, one of the alternative energy strategies we decided to go with was solar. As you can see, Milwaukee, Wisconsin is really adequate for solar analysis. It produces about 4.0 kilowatt hours per meter squared per day. And then our site itself is surrounded by only low-rise buildings, so that works really well. So we don't have to worry about so much shading on any of our PV systems, and that we can site our panels pretty integrated with our structure of our building, because only our own structure would be shading our panels if possible. And then something else that we wanted to look at when it came to solar evaluation was not only location, but also how much power can we get out of the panels. So we decided to look at a couple different panel selections, and we looked at efficiency curves per watts per square foot, so we could get the most use out of the least amount of space. So we decided to go with a SunPower 345 watt panel, and this works really well with the Living Building Challenge because this is within our 50% range for the materials choices for the cost. So it is located in Athens, Ohio, so that is good for that. And then for us to figure out how do we produce the most power on site as well, we looked at a shade study and as well as optimal angles for the panel. And originally we based our stuff on a flat-based roof because that was our original design. And 35 degrees was considered optimal for the location. And with the 70-foot by 20-foot base size, we could fit 56 panels at about a 10-degree slope and get the most power out of it. But in our actual building, when we pitched the roof, we kept the same 56 panels, but we had it at a different angle at 26.6, which is a 612 slope. And this is typical for construction, so this is good for a constructability standpoint, as well as for being able to fix the system if a panel were to break. And then this is also, the slope, it's also good for water diversion, and it helps improve the power performance of the PV itself. And the only difference for why we didn't go with the optimal angle and went with the 612 slope is the power percentage production increase from 25-degree angle to a 35-degree angle was only about 1.3% higher, which, as you'll see in a moment, we wouldn't need that additional performance. So this is where we decided to locate all of our alternative energies. As you can see, we have our building PV in green, and we have our solar arcade PV, which are the same panels but just different locations. And then along the east side of the site, we have the vertical axis wind turbines.
So we wanted to look at the payback period for this investment in the solar array. So basically looking at the power supplied by each module and the number of modules that we had, which was 560. We'd basically be producing 279 kilowatt hours per year. And the cost, which actually we got the price per watt from 2 watts, for the current pricing, and we looked up from NRO, the directory, basically to let us know where we can get some incentives to and grants to help pay for some of the installation. And they were able to offset some of the costs, which brought the actual payback period to 4.13 years, which is actually very good.
So also you can see from our PV siting where we have it on the buildings, as well as where we have our PV arcade in the front, we produce, like Israel said, 279,000 kilowatt hours in a year, and our building loads, which we'll get to in a moment, they are less than half of that almost. And so for the power production from the wind turbines, that's very minimal. They're more for the educational property to it, and they produce a grand total of 6,300 kilowatt hours in a year. So the reason why we're able to meet the 105% energy is because we have all those optimization controls. So we optimize the lighting, we optimize the devices and the miscellaneous loads, and HVAC as well. And in order to figure out a more realistic use of the building, we applied demand percentages to these loads based on the time of day and the time of year, depending on the spaces, and that gave us a total for the different space types that we had in the building, which was offices, market, gathering, classroom spaces, and then general administrative growing power facility, a grand total of 102,000 kilowatt hours a year. And so this is a huge reduction compared to the initial building loads. So the baseline building, like I said before, it was using 388 kilowatt hours connected load, and our building now would be using 138 kilowatt hours, which is a saving of 250 kilowatt hours overall. And our power density with all of our design loads is 2.76, which is almost a third of what was originally designed for in the baseline building.
So as far as the power distribution on the site, they do have the existing loads coming into the existing facilities here at that point. We talked to Wisconsin Energy, and they were able to step down the power to our facility to 120/208 voltage, so that we can 208, 120 voltage, so we can use that on our site. So it's a utility-owned transformer that is providing power, and it's basically connecting to our system right here in the basement. So looking at our one-line diagram, because our loads are so low on the building, we can basically have just a main distribution panel, which feeds our receptacle and lighting panels on each floor. And we do have the two photovoltaic arrays, which we'll talk about how they're bundled and connected to the system, but they're backfed into our panel to provide power. And Wisconsin Energy requires 2 meters whenever you have a power generation system, so that they can we can provide power back into the grid with our production. So as far as distribution in the building, our main panel is in the basement in our electrical room, as well as our emergency panel is in the room adjacent to it. This is our main shaft, which we're able to have because of the structure of the building and the design. And basically we're using those for all our vertical runs, and in between the structural bays, we're able to run north and south for our conduit runs in those areas too. So, and here we have our emergency generators. As far as the way the arrays are configured, we're able to find an integrated inverter combiner box, which kind of connects all the systems into one location. And one of the reasons it was good to have is that the power is actually inverted right at the array, so we don't have to worry so much about the voltage losses as you would with the DC going back to the field. And it has all the disconnects integrated into the inverter combiner box as well.
So for our PV, we decided to group it for the combiner boxes based on the building PV and then the solar arcade PV. And then the wind turbine energy would be supplemental to the existing building infrastructure as we showed on the site plan. So that would help power the existing building just supplementally in addition to our PV generation, which would then feed to their system as well. And then we only require 2. So our equipment room layout, as we said, the main distribution panel and then supplemental basement receptacle and lighting panels are in the basement. And then just adjacent to it is our emergency equipment panel in room. On the outside, where we have the incoming service from the Wisconsin Electric, it has a transformer, and it's situated with the structure, the 4-point structure is situated in there so that it won't be hit by any trucks or anything backing up into the building when they're doing loading and unloading for food stuff. And then our emergency generator is on grade on the outside, so it can feed the emergency systems of our building, and that's located just south. So we, like I said, in order for us to reduce our power loads, we had to do some type of receptacle control for our devices. So everything highlighted in yellow kind of just 50% of the receptacles are tied into the occupancy sensor of the space, and then for 50% of the receptacles are also turned off during the evening hours for any of the red spaces. And the orange spaces, they have no control because they'd be using most of their loads, typically 24 hours a day. Receptacle control also is similar for the 2nd and 3rd levels as well.
So looking at the emergency fire alarm system, since the building is only 3 stories, it actually made this more simple to do. We do have audible notification appliances and visual notification appliances on every floor. Only the basement and the 1st floor need address devices for the smoke detectors for the ducting in those areas because of the living walls.
So our security system, similar to like Growing Power, what they have right now, which is the bottom right picture, they have a very simplistic farm-like security system is the way we decided to design towards. So kind of like a dog protecting the chickens is the idea we want to go. So there will be high security spaces, medium security spaces, which will typically be like the back of the house, market or the food processing, cooler spaces, so stuff that the public wouldn't need to get access to, but helper volunteer could. And then the low security spaces are stuff that would be public to anyone in order for them to access. So those would be also the community spaces and the restrooms as well. And then for lighting, what I did is I went and did a lighting analysis using AGI program, and I compared the achieved lighting levels with my selected lighting design from IESNA. They give recommended foot candle levels and then my achieved foot candle levels. And I also compared this to lighting power density as received from ASHRAE and recommended also by the Living Building Challenge. And this graph is a good comparison for all the different space tips that we have. As you can see, the bottom brown line is what we're at, and the green line is the Living Building Challenge, and the top line is the ASHRAE recommended values. So as you can see, we're almost meeting or exceeding the designs that we were trying to shoot for.
So as far as trying to optimize the systems, again, we implemented some lighting controls in different spaces based on the usage, and took advantage of a lot of occupancy sensors and daylight sensors as well to make sure that those loads are running when they're not in use. So we have the different spaces where we have storage, basically auto on, auto off, because people will just be going in, dropping things off and things back out. Utility spaces, we wanted those to be manual on and auto off with a higher sensitivity because of people working on equipment or doing any extra work in there. We wouldn't want the lights shutting off on them while they're doing their critical task. And then the transition spaces, we wanted those to be able to have auto on, auto off with manual override if necessary for like the hallways and the lobbies to the elevator. Same idea on this floor as well. This is the parking area. We wanted to make sure that those lights are basically controlled by daylighting, but fully on whenever anyone is in the space, just for safety. In the office areas and the coolers are going to be dual tech, auto on, auto off, similar to the storage areas. The whole front section, the market and the vestibule area has a lot of daylight coming in. So we have daylight sensors for the fixtures in those areas. And the processing and service areas like the loading here would basically be mostly on during the working hours. So we basically control those if no one is occupying them. Similar on the second floor. Basically, these are all the growing areas, so we have a lot of daylight coming in there. And the back spaces as well. There's windows that allow daylighting in the back private office area, so that area closer to the exterior wall would have some daylight controls for the fixtures closer to the exterior wall, and occupancy sensors for the rest of the fixtures in this way. And basically similar idea for the third floor as well.
So this is just kind of an idea of my lighting inspiration. These are typical spaces that we have inside our building. So we have a market, we have some type of office, classroom, workshop spaces, and I was interested in using LED fixtures just because their efficiency standards are much better, and they help out with the watts per square foot that we were trying to shoot for. So the market, we actually ended up getting above the IES recommended foot candles, and we were able to get, our lighting power density achieved 0.89 watts per square foot, which is both below ASHRAE and the Living Building Challenge. And this was used using linear LED pendants with high CRI values because of all the food that will be in the marketplace. You want to make sure that they would have a good coloring to it, and then also with LED track lights that would put the light where we need to go for the displays in there. And then the demo kitchen has its own lighting as well, also linear fixtures, and we achieved the IES recommended foot candles for a classroom type space, as well as the ASHRAE and the very close to the Living Building Challenge watts per square foot for a classroom. And this was due to the our achieved levels is a little bit higher because of the hoods that we would need in the mechanical area. So this is achieved linear pendants, and as you can see, a rendering. The market itself, or the gathering space, is wanted to have 55 foot candles, and we got very close to the foot candle levels with my lighting design. And the reason why it's a little bit lower is it's actually good for the design area, and we ended up getting about a 25% reduction compared to Living Building Challenge, and about half the watts per square foot from ASHRAE. So that saves a lot on our total load for the building. And then this was done also with high efficient LED pendants and track lights as well. And then the layout itself, it was designed with interest and flexibility for the space as it would be used multi-purposely. So, and then some things that we still need to look at overall for our project is some telecommunication systems, and then our security distribution a little bit more in depth than what we have. Are there any questions?
Most of your slides were readily readable. There were several in there that weren't. Take a look at those. The other thing is, Israel, you got to learn your presentation really well so you're not constantly looking at the screen. I mean, when you're using the little red pointer, obviously you have to turn to the screen. But most of the time you don't want to be looking at that screen. Okay? And that'll come with a little bit more time. Diana, I and my, it's we and our. Slide.
There's no I in team?
Yeah, me team.
Slide right around 3. You said the electrical system complements other systems. It'd be COMPLEMENT. Just change the I to an E. Wind power. You guys were looking at the same kind of wind turbines that they have on this 1-800 law firm at Northwest, practically across the street here, at Northwestern and Lasser. One of those about 1 kW per wind turbine. They're cutesy. There are vertical, upside down, egg beater type wind turbines that are 65 kW. They're not 10 feet off the roof. They are 105 feet high, but you can put 10 of them on an acre, as opposed to these big 50, 100 foot long blades that you get 1 per 10 acres. So 10 at 65 on an acre of land is 650 kW, or yeah, 650 kW. So take a look at those. I can give you a website to take a look at. Might be something interesting to look at and make part of your presentation, because that big ugly thing that you had in there that you decided we're not going to use this, these things are nothing. And they'll work at much lower speeds, wind speeds, coming from any direction. And if you get over whatever it is, 50 miles an hour, 65, whatever it is that they have to kind of stop at, they fold in to the vertical shaft. So they're very, very cool.
That is cool. Actually, I can address that. One of the reasons why we didn't go with a different type of design for a vertical axis wind turbine is because as we were reducing the height of the building from 5 stories to 3 stories, we also wanted to keep our wind turbine height minimal too, to match for that.
Sure. Yeah. Right.
Yeah, well, this is a good question to ask, though, because that east side of the site is adjacent to U.S. Army Reserve property. And it's, I don't know how many acres that property is, but it's all residential to the north, west, and south. But on that east line where they've sited the turbines currently, that's all U.S. Army Reserve property. So I don't know, maybe it is viable that you put 100-foot slender turbines along that line. I don't know what you guys think about that, but just a question.
I've never heard of a 4-year payback on a PV system. I mean, some of the large government installations are 20, 50 years. So I don't know. Check your numbers. It didn't look like your grants were 80% or anything that would justify that big a drop, but it sounds too good to be true.
And that was like the biggest amount that's possible to get from the grant, because they do an evaluation for the loan, so I was kind of doing this.
But percentage-wise, it was only a quarter or something, so it's not going to take you from 20 to 4. So I don't know how you got to 4, but if it is that low, we ought to be doing that more.
Yeah, right. That's for sure.
You went over the need for an emergency generator. Right? What was the use for that, out of curiosity?
Well,
and how did that comply with the no combustion rules of LVC?
well, there's an emergency system required per the building challenge to be able to power the refrigerators and the emergency systems for up to 7 days. And rather than have a battery system that's sized for that, they do offer a on-site propane generator just for emergencies only. So that's where we decided to go with.
Okay, it wasn't defined very well in your discussion, just kind of went over it.
And I'm actually not even sure about the answer to this, but is it for emergencies only or for emergency services only? So is it, in other words, what essential services would be allowed to be powered with emergency power?
Basically the fire pump for the fire suppression.
And that's how you size the generator?
Yep.
Yeah. So, yeah, I guess explaining that
Yeah.
would be great. Because I had the same question.
I didn't really quite understand the justification for just jumping over the geothermal. I just went right to the wind turbine. So maybe a little more explanation on why that wasn't a viable option.
Yeah,
Well, I was just gonna kind of jump and piggyback along that question. It was a little confusing because from my understanding there is a geothermal system on site. So it's just confusing because I think what you're referring to is geothermal like steam, like
True geothermal.
True geothermal,
As opposed to geothermal heat pumps.
Right.
Yeah.
Right. So that was just a little confusing. Yeah.
Yeah, and most people, and these folks may not know what either one is, so defining those terms might be helpful. And using different names. One's geo-exchange and one is whatever, geothermal electric. I'm curious, in that slide where you show some of those samples, could you use a heat exchange? Because I know y'all were talking about doing some moving heat around.
we looked at a binary system, binary geothermal system. Most of the ones that we looked at were more for bigger, larger applications, like utility size. So as far as like all the equipment and everything that would be necessary for that type of system, we thought it was a little too big for our building. So that was more of the geothermal. That was one of the options that we had for the geothermal, as well as basically just pulling hot water and using the steam to generate electricity. So, but we that was a consideration, I guess, for looking at that.
Might you want to leave that whole geothermal thing to the mechanical people instead of you guys talking about it?
The geothermal exchange system would be like directly just the power, not just.
Oh, okay.
Yeah.
Okay.
So that's how we decided to look at it.
Oh, that's a thermocouple?
Well, the whole idea is we can't generate electricity.
Is binary refer to a thermocouple system? Where you have dissimilar metals at different temperatures?
Well,
It's
no,
like
no,
dissimilar
it's not dissimilar.
refrigerants, yeah.
It's basically using a heat exchanger to draw warm fluid from the ground.
Oh, okay.
And to do a heat exchange with a fluid that has a lower boiling temperature, so then you can use the steam to generate electricity.
So binary refers to phase change?
Refers to the two different closed loop systems.
That's a
And
straight
what
heat
they
exchanger.
Okay.
The phase change material circulating?
Yeah.
Is that what you're doing? Circulating the phase change fluid?
Oh, yeah, yes. Change it from the liquid to the gas.
Yeah, yeah.
So overall, I think this was all fantastic, especially some of the aggressive lighting controls and things. On the garage side of it, I was a little confused by what you were saying, that it would be needed to be on when it was occupied. Did that mean it is getting turned off? Because you said it was daylight controlled.
Right, it wouldn't be on during the day.
But that's it. That's the only control.
It wouldn't be basically just completely off because it is covered. So we just want to make sure there's optimum light in there, just for safety reasons, because it is an urban area.
Even when it's unoccupied?
Yeah, basically.
One thing I was going to take a look at the NREL garage system that they have. There's and these are actually coming really common, even in non-net zero energy buildings, where you'll have zoned occupancy lighting. So when somebody's coming up a stairwell, the zone in front outside of the stairwell will light. When a car moves, when a person moves to the space, these zones will be, the garage should only be lit when it's occupied. Lighting cars is just useless energy. And can be significant if you take a look at that over the year. I was actually really impressed, but a little cautious of your total kilowatt hour per year usage. So I'd love to go over that and see what the details of that are, because that's pretty aggressive and that was pretty impressive. I think you can get there, especially with some of these lighting controls and things like that, and as long as the mechanical guys come through with some really stellar stuff, it's going to be neat to see.
That's probably the biggest part that kind of pushed us towards lower
production. Right.
That should probably be said too, because you know, I never heard anything about integration with the other systems, and especially with mechanical, because mechanical and electrical are so closely tied together.
I just had a question, I guess, and this is going back to, I think someone had mentioned it earlier with putting north arrows. I'm sort of confused about like your use of like where you're using daylight harvesting and what orientations of the building, and then what is actually being, those spaces are being used for. Because you want to be careful if that's on like east-west axis and you have like direct morning and night sun and those are like office areas and you haven't addressed really mitigating glare yet. So you might want to consider like what those spaces are used for on what orientation and how you're going to actually like use that sunlight so it's not quite so producing so much glare, or so people won't actually be able to do their jobs or learn or whatever in those spaces. So maybe take a look at that with, if you guys think they're kind of like sun studies too. So like where that's hitting.
The way the building is oriented too, most of the office and administrative spaces are to the north.
Right.
So most of the sun would be good there. Not so glaring.
Well, in the classroom, so
yeah,
gathering space.
So I mean, if you look like a sawtooth daylighting system, they're not open to the south; they're open to the north.
Right.
So that you get that ambient light reflected down in there. So.
Right. Is that the long access? Is that your one?
Yes.
Okay.
Basically, it's on the top.
Okay. Does that seem like it was along what would be like south or like gauge orientation is where you had like a lot of your daylighting designated on your diagrams? It seemed like so. Lots of caution, be careful with that much.
You just need to be more clear.
Yeah. And then address glare.
The 50% of the lighting of the plug load receptacles being turned off when they weren't being used on occupied hours, what have you, is that a living building challenge requirement?
It's not a requirement.
It's not? Okay.
But
it's just, go ahead.
It's just a design consideration.
Okay.
Because we're looking at the spaces by how they'd actually be used.
Sure.
So,
Well, it's a good idea. We tried to get it in ASHRAE Energy Standard 90.1 2013 and got shot down. But we'll probably get it in 2016.
And the program of the building really helps a lot because it's a greenhouse.
Right.
And it's supplemented by these offices and these
Sure.
classrooms. So, but it's about growing plants, and
Yeah,
that's all just a natural
that's a
thing.
good move.
Just a couple stylistic things. Again, I think this is going to be true for everybody. Fewer words on the screen, larger font, highlighting the key points of each one. The wind survey you did, it was literally too small for y'all to read where you were standing. So to us, it becomes completely irrelevant. A simple thing like a windrows showing these are the wind patterns. Any fifth grader could understand what that means. Here's where the wind's coming from. Look at each one of the slides and see what way you can visually represent the key points of each one of these slides without so much data that is not going to be, we're not going to have the time to explore that in a presentation. And also, I was hoping somebody else would say this, but you have a great voice, and you didn't use this. I want to hear your full voice. There were some times where we couldn't even hear you back here. So use your full voice.
Do.
There you go.
Speak from the diaphragm.
I was also going to say, when you show data, try to show it consistently on slides, because you had lots of charts, but they were all formatted differently.
That's right.
And you had bullets, but they weren't consistent from slide to slide, nor were they consistent with how structural showed it. So try to get the whole presentation to be formatted consistently.
That's right, like every slide where you have that key piece of data, put it in the same location in each slide. Have the same types of charts in each slide. so that visually we're not having to our brains aren't having to reabsorb and relearn for each slide.
And along those lines, I did notice on the building load slide, you had 2 pies for your baseline building and your building that, like the HVAC was different colors on each one of those. So at first glance, your colors were darker, and it actually looked like the baseline was smaller. That there was, so it kind of, just the graphics being confusing, it actually made me think that the baseline was the better situation of the two.
Yeah.
So.
I just had a couple of things on your lighting scheme and daylighting and integration, and I know I heard the same thing from others. It's not clear to me, or if you thought of light shelves or other things, what are you doing to maximize and harvest daylighting, bring daylighting deep into the space, so that you're not just saying, okay, here's linear fixtures to make up for it. So I think that really innovative, integrated thinking to say, because they're having to do this structurally, and because we have this opportunity mechanically, and because we want to have natural ventilation, and because we want to have that kind of light, because we're growing, this is what organically came out of the lighting scheme that we wanted to go with, and being able to do as much without electric light. I mean, you're working so hard to generate power. So talk about why you can do it without it. What can you do without it? What is the building allowing you to do without it? I think just along the lines of what everyone else is saying, I know we haven't heard the last presentation yet, but I think that the team said this last year, others said gave the same to the team. When you have your first slide and you guys always have those couple of bullets up there of what you're going to kind of go through, that's great. That's what you're going to go through, and the other team went through something else. So when you all get together again, what are your big themes? What's the story you want to tell? What's these 5 things, and then whatever you go through structurally, and whatever you go through electrically, and whatever you go through mechanically, somehow it's touching back on, you're hitting back to those things. And then I think you'll come back around and you can summarize it too. So in your intro, you hit it with each one of the systems, and then it closes you out as well. And I think, it was said again, but just visually, it seemed like there were some slides you made and there were some slides that you made. But I know that's work in progress right now.
I had a couple things. Again, I thought images and presentation was great. I liked the upfront stuff about the alternative energy and what you guys were looking at. But after that, what's the next sexiest thing about this project? It's the lighting. And the lighting was way at the end of the presentation. Get that up front. That's next. Get that up front. And I wouldn't put lighting control before lighting. I was always waiting. Lighting control, and I said, do you do lighting? Because you're already controlling it. Put lighting control after it. In Israel, tell them why you're doing lighting control. ASHRAE 90.1 says I have to do this, I have to do this. Tell them why you're doing that. Fire, security, and telecommunication, that's boring. Get in the back, in my opinion. We don't need to see that up front. Electric equipment layouts, I think you had equipment layout. You had equipment twice on that slide. In ATS for emergency, do you have other than life safety loads?
No.
Okay, I thought I just heard something about refrigeration on the generator.
Yeah, that's what we're saying.
Is that considered life safety though?
No.
Well, that's,
Because then you'll need 2 ATSs then. 2 automatic transfer switches then.
Does Living Building Challenge allow the refrigerators to be on the generator?
Yes. The refrigerators are basically the freezer coolers, which are holding food storage stuff. So it's not like a life safety concern.
So you need 2 ATSs then, if you're doing lighting also.
Lighting,
lighting is an emergency.
battery ballast.
Oh, okay,
That's the
great,
way we wanted
okay,
to do that.
okay. Good.
A couple of things. Liz mentioned it, but in regards to color, pay attention to what colors you're using, and in some of your graphics, I think it was the facade was very, very bright green, which is a little distracting from the electrical equipment that you guys are trying to highlight. Some of the lighting control graphics, there was a brown and a yellow that looked almost like the same color.
Yeah, it's something like that.
And it could just be the projector, but you'll wanna take a look at that.
Take that into account.
Yeah. And the other thing is, so the living building challenge requires a lot more. It's more energy intensive than even ASHRAE 90.1 is, but I think using ASHRAE 90.1 is a good baseline. And I think the newest version of ASHRAE 90.1 is using more so what you would consider a vacancy sensor than an occupancy sensor. So it's more of a manual on and automatic off. So it requires the user to turn it on, and whenever it's vacant, that's when that's detected. Also pay attention. I couldn't quite tell, but it seemed like a lot of spaces that had equipment on it, or where people would be working, that there were occupancy sensors, which you don't really want. You'd rather have that just be a manual on and manual off, because if it can't detect that minute control or that minute motion that is going on, then it could go off, and that could be a safety issue.
I'd just like to piggyback on that. The occupancy sensor would be required by ASHRAE in all the working spaces. You know, in offices? Or it'd have to be on a time control.
No, I mean like equipment, like electric rooms, mechanical
Oh, I thought you were saying in
rooms.
working spaces when they were
No,
sitting at desks.
we're specifically like
Oh,
equipment,
Yeah,
utility spaces.
So, well, basically the intent was to have like a higher sensitivity motion sensor that would, basically if you turn a page, it'll, stay.
Well, I mean, yes,
So,
I agree in the
but if
offices
in
and all
most
that,
cases, you just have manual on, save money, as far as installation costs, I'm sure, but, I was just thinking as far as like, okay, what if the guy's in there and he wants to go to lunch and just leave it on the whole time?
One of the problems with occupancy sensors is people are getting so used to them that in the areas that don't have them, they're not shutting the lights off. This is happening more and more because people are, I don't have to do anything. There's an occupancy sensor and it'll shut it off after I leave. Not if it's not there. And that's happening.
Again, maybe I missed it, but being this a greenhouse, were there grow lights in this?
No,
Why?
because all of our spaces, they have top lighting. There's no covered growing spaces, so they're very similar to the greenhouses that are existing on site. So we didn't account for any type of grow lights.
And grow lights are carnivorous in power consumption. Yeah.
Well, they may be, but again, I look at the question, why would you go and leave, they're paying very little rent in this place. Why would they go to a place where they're not going to get any more productivity than they are right here? I look at it from a business viewpoint of why. Somebody's got to explain in this presentation what the advantages are of this new. And it goes back to what we talked about last year. Why would you do this? There's got to be something in your design that's better than somebody else's.
Yep. Yeah, you have winning ideas. You have to convey it like these are winning ideas.
And the growing lights that we did look at, not only
It doesn't, you don't have to, all you have to do is to be able to give the reasons why this design is better than others. You don't have to necessarily answer my questions. You have to tell me why I should want it.
I just wanted to share something I think that we all experienced. The team from last year after our second crit that we had kind of right before we went to the competition, which you guys will have obviously at the end of the semester before you go or whatnot. And that was a lot of what is you guys are getting this feedback early. Go through, we literally afterwards tore our presentation apart, deleted every single word we could possibly delete from every slide. It's true. We seriously, does this absolutely have to be here, or can we say it? Are we going to say it? If we're going to say it, it doesn't need to be there. If you're going to say something, it doesn't need to be on your slide. What image can replace these words? Because images speak to people. So the more time you have to do that, I mean, we had literally a day and a half to do this, and it was insane. And you guys definitely have the advantage of having 2 months to say, I don't want these words, I don't need this chart, I don't need all of these numbers. I mean, yes, we're engineers, so we love our numbers, but remember that you know, you're going to write a report, and your report's going to have all of this information in it. You want something that people are going to remember, and they're going to remember images, and they're going to remember the inflection in your voice, the way that you speak, what you're passionate about. And they're not really going to care about, you know, the chart that you had on slide 4. They're going to remember, you know, you as people and like the images and the product. It's a product that you're, you know, selling them on. So, just a little summary of our pain in the final hours.
Any final questions?
No, good job, team. All right, take it over, mechanical team.
All right, last but certainly not least is mechanical. So a quick overview of our presentation. We're going to talk about climate conditions, particularly pertaining to our 2 site locations. Building loads, our facade, which will bring us back, hopefully answer some more questions pertaining to structural and electrical. Our heating system, cooling system, our living wall for our outdoor air requirements, our rainwater collection, and plumbing system.
So as a mechanical team, how do we directly affect and can we take from the Living Building Challenge? So one of the biggest ones is net positive energy. How can we reduce any of the energy we need to use throughout the building? And then also net positive water and net zero waste, meaning all waste has to be treated on site and not disposed of into city sewer lines.
So design goals for our mechanical system particularly revolved around, we are designing a farm, not a pharmaceutical. So when we visited Growing Power, it is very specifically a farm. It is not it's a business, but it is not a factory. They're not just producing goods. It is a farm. There are people. There's a community system there we wanted to design around. We needed to focus on reducing our energy consumption, working with only the energy we had available specifically to farming, and that farming, the energy that farming produces, and then also following, understanding biomimic design, that we need to understand how nature works and how can we design our mechanical system to be the lungs and the veins of a building. So pertaining to our 2 site locations, Milwaukee is in Climate Zone 6A, non-residential, which is a cold and humid environment, much like what we have here. So we have a higher set point of 89 degrees and a lower set point of 78 degrees in the summertime. And in the wintertime, it was important for us, I wish he was still here because this goes right along with what he asked about the greenhouses, but I was really excited about it. But in the wintertime,
Tell the chair.
in the wintertime, we wanted to design a greenhouse, a building of greenhouses that you could have plants growing all year round, which is what they do at Growing Power. And with our mechanical system, it gave us the ability to grow every day of the year, regardless of the temperature outside, but at a minimum of 58 degrees Fahrenheit for either location, which means that our heating loads and cooling loads are really minimal in the greenhouses because we want to maximize our growing area.
And by doing that, you're not forcing something to grow that's not usually grown in the wintertime. You're not forcing tomatoes that need 90-degree weather to grow when it's 32 degrees outside. You can maintain and grow cabbage, kale, broccoli, stuff like that in the wintertime, which is normally grown during the season.
So talking about precipitation, Milwaukee, which is right here. I should make that bigger. That's hard to see, isn't it? Is that hard to see? Okay. Milwaukee has an average rainfall per year of 34.73 inches, which is very important for us as far as rainwater collection and having net zero water for the site.
So structural, when they started going over different wall enclosures for the building, they started to ask questions of, well, where should we look for different materials and what R value should we be at for the wall. So we did a quick energy analysis between different types, total R values, and found that once an R20 was reached in walls, it was basically the point of diminishing returns in your heating and cooling loads. Maybe it decreased by 1%, but that was about it. And then same thing occurred in once you reached about an R30 for the roofs. So anything after that, to over-design those walls, wouldn't be worth it. And window-wise, in the greenhouse, we originally considered an ETFE system, and our polycarbonate, while doesn't necessarily meet where the ETFE stood R value-wise and the decrease in loads, it ended up being more cost-effective option for us to consider. And then energy model-wise, we had a design for a total building cooling load of 45 tons and roughly 700 BTU heating loads.
So this is an overall building system diagram. This is our heating side, cooling side, and our water side of the building, and then revolves around this occupied space. And we'll break down these systems later on, but what essentially happens is there's a closed loop that's created for every single system that revolves around the occupied space. So we have a heating system that's radiant, a cooling system that's also radiant, a rainwater collection system that supplies every fixture in our building, and revolves around this great living wall that supplies all of our outdoor air, but mainly that it's not just about these systems, but it's about the people in these occupied spaces that the system supports. So talking about our heating system, compost is very prevalent at Growing Power. They generate 20,000 tons of compost a year across 4 farming sites in Milwaukee, which they don't have the area on site right now to generate all of their compost just in Milwaukee, or just in the Growing Power site that we're talking about in Milwaukee. So it was important for us to understand that using the heat source on site, that we had a heat source on site to utilize. So compost, when it decomposes, it's a chemical process, and I can get into all the nitty-gritty because I've done an obnoxious amount of research, but I don't want to bore you. But the main point is that you can have a good batch of compost or a bad batch of compost, but all of them will generate heat. But if you can optimize the type of compost that you're using, which right now they use materials from, or waste materials from local restaurants and other farming areas in the community. And if they can balance this carbon to nitrogen ratio, which maximizes the heat production from the decomposition process, they can get 1,500 BTUs per ton per hour from the compost, which gives them a viable heat source that's already on site that they don't even have to dig for. It's right there already for them to utilize. So we've proposed to use this compost heating system, which would be located in the back of the site on the north end of the building, which would be housed in a similar construction to our building, one of the bays. There would be 2 bay systems that we would need in the red squares or rectangles up above. The compost can be staged so that it can be housed in these two constructed bays and moved throughout the facility, so that there's enough space that you can move throughout the facility still and have the 400 tons of compost that it would be required to generate the building load. So the way this system works is, the compost sits on top of this aerated pad, and then there's a fan that pulls through the air through the compost, which aerates the compost, which is good for the composting process, and also pulls heat through the compost and into the building, into what's called an isobar, which generates heat for our radiant loop, essentially. And this is a schematic of the isobar, which basically takes your gas as a heat, and it's a gas to liquid heat exchanger. So in our mechanical room in the basement, this large square over here, it requires a 8 by 8 foot footprint with a 4 foot clearance all the way around, is our isobar heat exchanger that would serve the 400 active tons of compost and would be piped into our radiant shaft on the north end of the building, and then that composting enclosure would be right on the north side of that drawing.
So now that we had taken care of all the heating hot water in the building, it was how do we get cool, chilled water. And if you have an evaporator type anything, we would have to account for all that water in the living building challenge and where it comes from, and then it evaporates, and how do you put it back into the system naturally. So we decided to use a geothermal type system to chill the water. And we decided to go with a coil slinky system that would run through the back of the site, because we ideally needed it for cooling and cooling purposes only. So it made more sense to do something like this versus doing a bunch of boreholes, which you could use more prevalently when you needed heating. So we used our trace energy load and the GLD software, which is a ground loop designer. to analyze how much of this coil would we need on site. And so it was found that we would need roughly about 20 to 50 actual feet of trench dug out, but they would be 36-inch round coils spaced 6 feet apart. So when we were talking with the structural team about how they would want to stage construction throughout the site, it was where would we ideally want to dig that so that we don't have to backfill and dig a giant hole and that would mess up construction. So underneath the building, we're already excavating parts of the building, so why not try to implement some of that geothermal loop where it's already going to be excavated. So that's what's here and here. And then along the back site, we'd originally proposed to only go up to this point right here. And while feasible, to get the 4,200 square feet of trench that we would need to dig up the entire backside of the site. So you'd have to dig 6 feet down an entire trench, which would make it hard for construction because you'd have to do all of that before you could do anything else, and it would have to be backfilled. And so basically then, once the geothermal loop comes into the building, there's 2 water-to-water heat pumps running at about 25 tons each. And so as the hydronic system loop together, we did realize that typically the geothermal loop is going to be heating at points too. You can get heat out of it. So if it was at the compost, we didn't have enough tons of compost at the time to heat the building, we could tap into that geothermal loop and the return water from the chilled beams in the space to help pick up any of the load. And so when we were looking at biomimic design and how does that all work with the mechanical system, well, how does nature clean air that we breathe naturally? And so they use plants, and the plants collect dust and they filter it. So there's a system, when used appropriately, can actually purify, oxygenate, and clean any chemicals from the air. And what happens is when the air is drawn through the plants, as soon as it reaches it's a hydroponic system, and because the air is able to have direct contact with the roots in the system, that it can clean and purify all the air, which then can be recirculated back into your building and used as your outdoor air ventilation, which is minimum requirement. And with that, then we don't have to bring in negative 10-degree air in the middle of wintertime. We can just recirculate the air that's in the building that's already been conditioned, which would reduce the total energy we need in the building. So this is just a typical wall of what it would be. It's all plants along the front face, and then it goes through a manifold which leads it up to a duct plenum which can go through fan and coil after that. And it can be sized at roughly 10 to 20 CFM of fresh outdoor air per square foot of growing area. So in our building, when we started going through loading and everything like that, we had originally sized a footprint of wall for the minimum ventilation that we would need. And so we'll get into later the process we went through with the loading, but it basically ends up we have one central wall that goes all the way up from the first floor to the third floor. And it's two-sided on the first floor, and a lot of the while it doesn't need all that square footage to cover the first floor and basement, it was part of that whole beauty pedal in the Living Building Challenge, and you walk up and you go to that market and you enter the lobby space, and there's this living wall there, there's these plants that's part of the building. And then it's one-sided on floors 2 and 3. So this is the second floor, and everything spans and branches off from that central living wall for all the air distribution. And we ran into some problems when we were designing the gathering space, because it needed to be designed for over 400 people, so there was high loads in that space. And when we were going through iteration after iteration, we didn't have the necessary growing area on that second floor wall to cover all the classrooms, which could be fully occupied at the same time that the gathering spaces are fully occupied. So what we transitioned to was using 2 smaller walls in the gathering space that would solely serve the gathering space and the gathering space only, and then the central wall on the second floor would serve all the classrooms and the couple incubator offices on that floor. And then again on the third floor, the central wall feeds all the offices.
So during part of our initial research, we looked at a lot of solar chimneys, thinking we could utilize this natural ventilation in the building. And then once we did our floor plan, we didn't really have anywhere we could put this natural ventilation. And natural ventilation basically allows you to let the building breathe. So in the summertime, you draw in cold air, and in the wintertime, you recirculate that warm air. that's already in the building from the latent loads. However, for us, we didn't have a place we wanted to have this giant central atrium, and after we'd got the floor plans done, we didn't have anywhere for this central atrium, and so we were looking at a section of our building, and we thought, okay, well, we have all these greenhouses, why can't we just use that as our solar chimney? So once we were looking at air circulation in our classrooms, if you open up an operable window, which for comfort for people, if it's nice outside, open up the window. You don't have to have all of the space conditioned all the time. It lowers your loads and allows for this natural ventilation. And if we add transfer grills at each wall penetration in the corridor spaces and open up an operable window in the greenhouse, you have a nice natural flow of air right through your building, which you know, makes people comfortable.
And then instead of adding something to the building, like a solar chimney, you're already utilizing what the building needs to do another process for the building.
So when we started our typical space design, we initially wanted to use these radiant panels in each space. We had hot water, we had cold water, and we needed to serve the space. So we started off with a typical occupied space, your gains from your exterior, or loads from their exterior, and we had a radiant panel served by our hot water and our cold water, our filter acting as our living wall, and a fan, and it was just this nice natural circulation of air. And then we realized that by using these radiant panels, we're not satisfying our latent loads in each space, particularly in spaces like the gathering space and the market where we have higher latent loads.
And so when we originally went through and we were starting to size these radiant panels, we were trying to keep that ceiling space open so you could see the underside of the deck and the steel and how everything was constructed. Well, we need a radiant panel almost the size of, like, basically the square footage of the entire room. So that means the entire ceiling space is gone. So then we went on to variation 2.
So we utilized a chilled beam in this variation, which gave us more open square footage on the floor plan, moved the conditioner essentially for the space up in the ceiling, and conditioned the air immediately outside of the unit so that it was picking up our latent loads. But once we circulated the air from the chilled beam through the filter up to the fan, we still weren't satisfying the loads that we needed, and then we had a humidity problem. Because once we came out of the chilled beam, we were picking up air from the filter, going through the fan, and just naturally creating a very uncomfortable situation for the occupants.
So then we went on to variation 3, which was, okay, we have the fan, we have the chilled beams, but we'll add a cooling coil to help take care of all the latent loads. But when we were going through the calculations for this cooling coil and the latent loads, we ended up increases the CFM way more than the minimum outdoor air to meet the latent loads in some of these spaces with all the people, which then defeated the purpose of having a living wall that only needed to supply the minimum outdoor air, and then we would have to increase the fans. So this option led to, and by the time we were adding that extra CFM, we were way over where we need to be for any sensible loads. So it was kind of defeating the purpose of reducing the CFM to begin with. And so the last iteration that we're at is, a big thing for us was to try to not have a big central air handling unit in the building, so to have it by floor right off the wall. And so we came across these heat pipes. So they're wraparound heat pipes, and as the air comes into the pre-cool, it pre-cools it, goes to the cooling coil, and then reheats. And so it's completely passive, and there's no pumps involved. And as it loses heat from the pre-cool, and then it can be overcooled to account for all of the latent loads in the space, any of the heat that was lost in the pre-cool can be added back in the reheat to help dry the air at the end. And then all condensate from that can be routed right back to the green wall, which needs the water to recirculate back in space, in this closed-loop system for water.
So we ended up with this final occupied space. There's no more, we promise. And basically what happens is when the air leaves the space, it's filtered by the living wall, moves through the fan, moves through essentially what's a preheat coil, a cooling coil, which handles our dehumidification off of the wall, and then a reheat coil, which now has our air at our set point, to then go to the chilled beam, which will pick up the latent load, and then it just continues in each occupied space depending on the loads in that space. And what ended up happening is by adding this heat pipe, we essentially turned our building, the entire building in each occupied space, into its own air handling unit. So we have our intake, our filter, which is the living wall, our heat pipe, or our heat pipe, which is essentially the reheat coil or the preheat coil, depending on what air handling unit you have, and then a cooling coil, and then the fan to the occupied space. So we had this this is our favorite part of the presentation, by the way, because it was a great process of discovery through our design, but when we got to this point, our main goal was to not have an air handling unit in the building and to not use all of these giant systems that don't work efficiently. And once we realized that we did this, we turned the entire building into something that we didn't want originally in a way better way. So it was very effective.
And then I think we have erased probably a bunch of times on the same cycle chart of how we were trying to get that closed-loop cycle to work. And so finally with the heat pipe, we have our set point at 78 degree dry bulb, 50% relative humidity. And then the heat pipe can pre-cool it down to 71 degrees, so that's free cooling that you have. And then your cooling coil only has to take care of a delta T of 18 degrees versus going from 78 all the way down to 53.
So having these radiant systems in the building, we have a lot of piping. And being an educational building, we have all our shafts designated for each individual space. We utilize this aquatherm piping, which has a designated color for each use type. So we have green pipe that covers our potable water, so for all of our water distribution in the building. Our lilac pipe, which would be irrigation and rainwater. Our blue pipe, which would be for our geothermal loops and any associated systems. And then the black pipe, which would be for all of our radiant piping throughout the building. There's a 6-year warranty, so it's really good for lifespan. And then the color designate the pipes, so if you've ever been in the Taubman building on campus here, everything's labeled. You can see all of the systems, and it's very interactive. So in a space like this where you have classrooms and greenhouses and kids running around learning about all these systems, this piping allows you to see where everything is going and understand it in an interactive and fun way.
And this also meets up with the material pedal for the Living Building Challenge, because Living Building Challenge says we can't use any type of PVC piping. So this is a polypropylene product that can be used in its place.
So when we talk about rainwater collection, we have to talk about building usage for our fixtures and our plumbing. So we divided up the building into 3 different case usage types. So we have one usage type of a large event usage in the building. If there's the gathering space is at full occupancy, the classrooms are full, the workers are all there, that's going to have a certain load and will happen a certain number of times a year. And then we have a medium event occasion, so kind of the same thing but a little less people, that will happen a certain number of times a year. And then an average occupancy, which will have maybe like 50 facility workers and 20 visitors per day, and that would be typical of most of the year. So we compared this with our baseline building, and utilizing the same value or the same amount of irrigation water on site, which ended up being 50,000 gallons of water per year for irrigation outside of the building and inside the building, and the additional building, the existing building. We ended up with a 65% reduction utilizing the irrigation, and if we don't take the irrigation into account and we're just talking about the fixtures, we had an 85% water reduction, which is really good considering we wanted to be 105% on our water usage. So talking about rainwater collection, we discussed before in the structural presentation about how we're going to channel this water to collect it and how we can utilize those channels among the bays. So in this graphic here, we have, these are all the peaks on the bays, and then another peak here, so the water naturally flows off of the peaks into these channels between each bay, which actually coincidentally Growing Power does right now. They collect all of their own water, which you can see up in the picture up there. They have channels between their hoop houses so that you can collect this water, and it flows right between the greenhouses and goes right into their collection cisterns. So that point for us is right here on either side of this bay into our 4 rainwater collection cisterns. So with our total roof area, we can collect about 500,000 gallons of water a year, which is great for us considering we have all of these plants that we need to water. So given the amount of water that we need per year, which is about 60,000 gallons of water, you need one 10,000 gallon tank for every 40,000 gallons of water that you have on site. So considering we're able to collect so much water, we put 2 of those 10,000 gallon tanks for collection and 2 for after they're filtered and purified. So this is our filtration and purification system. It's an aqua treatment service which goes right along with our Living Building Challenge they're able to filter and then purify the rainwater that's collected on site. There's a rainwater collection spout, and then the gray water from all the plumbing fixtures can tie right back into it, so you're just continuing to have that closed loop cycle. Then there's a bypass that can come off that can go right for your irrigation outside of the building because you don't need to purify that. And then the water will go right into your collection cisterns until it needs to be purified or to fill up the potable water storage. So it'll go through a purification process that involves essentially ozone filters and a series of pumps. And once it goes through that, and it can also have chlorine associated with it, but given the Living Building Challenge, chlorine is a red listed item. So we studied a building, the Chesapeake Bay Foundation, that had a rainwater and filtration system on site, which they didn't want to use chlorine because they were following the Living Building Challenge, but they were able to kind of bypass that because they said, we're able to do it, so they had to put one in just in case, a chlorine system just in case, per code, but then they didn't use it unless someone came out and said that they had to. So it was there just in case, so you can do it without chlorine. And then it goes right into the potable water storage, which would go right into your building uses. So talking about composting again, we have compostable toilets in our building. We have 13 compostable toilets associated with each floor total. So this is an example of one of the composters. I don't know if you can see it back there, but you're supposed to be able to see through it. So the compost is collected down here. This is an overall view, and then there's a motor associated with it. Because we have a 3-story building, typically you'd have to have a composter right next to the composting toilet. But because we don't want to take up all of our square footage with these composters, we found this toilet that allows you to have this vacuum pump associated with it, that you can pump this waste up to 70 feet away in any direction. So we have a main shaft here in our associated with our mechanical space. We have 5 composters in the basement that are all interconnected that hook up to the toilets so that they can go to whichever one is available or full, and then they have to be emptied every so often, which might not be the most fun job, but can be recycled and taken out to do composting outside of the facility, because according to the code, you cannot use compost from composting toilets inside of a building for food growth.
And this was one of the opportunities, the challenge was during the design of the architecture, and as we knew we had to use these composting toilets, so that was a big part of how do we get every single toilet in the space to be able to get to that shaft. So back to the floor plans, all of our toilets are stacked right in this general vicinity so they can access the shaft. Versus a couple of iterations, they were across the building and you would need 2 composting units just for 2 toilets that are on the other side of the building, which wasn't very good. And so some of the things we still have to work through on a design is right sizing of all the refrigeration units in the building, because we know those are going to be a big energy hog for us. Doing a good comparison between their baseline case versus our baseline case using just 90.1 standards. We originally did it in the very beginning, and we were about 16% difference in energy savings from just switching from the 5 to 3-story building. But we have to go through that one more time. And then obviously equipment selection, and we'd like to eventually do a CFD analysis of the greenhouse to show that we're going to get adequate airflow through there for all the plants and life cycle costs.
We initially did our trace loads too, but now once we're using this composting system and geothermal loop and all of these kind of non-conventional systems, you can't just stick that in trace and get your loads spit out. So we have to kind of go unconventionally around that to get our loads to have a good comparison. So we got those systems finalized almost, and so now we're able to go back and do our energy analysis.
Cute. Okay, one comment. You guys are using American square feet and things like that. I think the structural people used meters. You guys need to get together on that. Decide which way you're going to go.
We used feet. The kilometers was for the Living Building Challenge.
That's what it was.
Okay,
okay.
We used feet for all of
I thought I saw some square meters too.
No? No? Well, of course, you had the circles with kilometers on there,
Yeah.
but you also had miles
We'll change that to
underneath it.
miles.
Yeah, we'll change that to miles.
There's miles underneath it. I could have just set it by miles instead of kilometers.
And there were a few slides, probably not in yours, that use some, whether you want to call them Canadian or European, OUR instead of OR kind of things. You might want to change those too. They probably were from wherever you got the source was probably a Canadian or a European source. You might just want to think about changing those couple of things. Have you guys figured out what temperature water you're going to need for those cooling coils in order to select your chillers?
Yeah, so we have 50-degree leaving temperature from the water-to-water heat pumps, and those go right to the cooling coils. And then the bypass between the return water from that and the return water from the chilled beams itself can supply out 60-degree water to the chilled beams.
Well, be careful, because 50-degree water isn't going to do any sensible cooling. I'm sorry, any latent cooling.
Okay.
So you're worried about, getting rid of that humidity. You're not going to do it with 50-degree water.
Well, what we're able to do too, because the loads are lower naturally because of the laid wall. So we're not bringing in air that we have to condition twice. So our outdoor air is naturally almost at our set point already because it's being recirculated through that wall. So by utilizing the 50-degree air through the coil and through the chilled beam, it does pick up our sensible load because the air is recirculated.
Well, it'll pick up your sensible. What I'm saying is it's not going to pick up your latent probably. Because what you're getting through that living wall is a dry bulb temperature. You're not getting much difference in wet bulb. So be careful.
Okay. Yeah, we'll look at that.
And I think you mentioned the living walls providing your outdoor air. It really provides your ventilation air, right?
Satisfies our outdoor air requirement is what it probably should.
Or ventilation because it's equivalent to outdoor air.
Yes.
Right?
Yes.
And then return air path, doesn't that need to be above ceiling or ducted?
Yeah, that was actually one thing we're trying to work through is how we can get the air from the spaces back to the living wall without it directly going through a corridor.
Yeah.
And then the chill beams do require a safety cushion in your relative humidity in the room. So I would think that you would want lower. I would agree with Jim's comment on the temperature.
Okay.
And be careful with the chilled beam, because if you do get that water temperature too low, you're going to get condensation off the bottom of the chilled beam.
Right.
And drip all over your rooms.
Yeah, and that's one thing when we were going through it at our set point, we were 2 or 3 degrees above dew point for the water going to the chilled beams to hopefully avoid that condensation in the chilled beams.
That's real important.
Yeah.
And one kind of recycling you might not have addressed is if your wind turbines kill any birds, you might be able to feed the birds to the goats.
We'll put that on a slide.
Those kind of wind turbines don't kill birds, though. They're very bird friendly. The birds can fly in and around.
Put them in the composter.
Just throw them in the compost.
I mean, I'll let George and Jim comment about the technical part of it, but I thought the presentation was outstanding.
Yes,
I mean, your energy was great, and the way you played off of her back and forth was outstanding. That was great.
I forgot to mention it. I agree. Yep, absolutely.
You're up there kind of dancing with your energy, and you sit there calm. I mean, it worked nice.
You really made it your own, It's like...
I mean, we had fun with it.
We had a lot of fun with this project, especially, I know it's so nerdy, but once we had that air handling unit, it was exciting because we really met one of our goals, to not have an air handling unit in this building and to have an unconventional system work really well. And we went through all those iterations, and we were really determined to make it work without having like 6 different systems trying to make one thing happen. So we're very happy with our progress. So we have a lot more to do, but we're very happy with where we are so far.
You should have saw her dance when she realized it was way better than
I think everything we figure out has a dance associated with it some way.
You also said something that struck me that to me, I'd love to see you highlight that even more. You asked the question, how does nature clean air? And it's like, and you should let people think about that for a second. That deserves its own slide. I think it's a really compelling, really inspiring question, and will score you some innovation points too. How does nature clean air? That was awesome.
Biomimicry is very cool. Very cool.
Yeah. Oh, and to that note, you said the word biomimic a number of times, and you had it on the slide. It's biomimetic. Biomimetic. So biomimetic engineering is the term. Yeah. Biomimicry is the field, and biomimetic is the.
Oh, I was just in the chair.
You know, how put the sexy stuff sort of at the beginning. I think the way that you the way you sort of took us to the point of getting to that air handler, you know, you sort of, it was kind of like we're just on our edge of seat. Okay, what's next? Okay,
yeah, right. That's right.
And so it was really, I thought that, you know, you just played that really, really well. I know you have some work to do still, but I'm just, for the fans and the pumps that you have still, you know, and what are you going to be utilizing, and how are you, what energy, and I know you still have work to do there, but it was great to see the other systems, and I thought, well, how much, you know, what are the size and how much energy are you going to end up utilizing for those?
Yeah, our system design, just getting to the point where we knew it would work, took a while. So now we're at the like just a couple days ago, now we're at the point where we can take these loads now, we know it will work, and we can find something that's efficient that will support it effectively. But before we could do that, it didn't really make sense for us to be sizing things, which, I mean, to go right along with our distribution, we really want to work with that linearity of the building, and we just didn't get to a point where we could make it work effectively yet, that we could really follow up and support that. So it's on our to-do list.
And I didn't hear the synergy of putting the slinky loop along the creek.
Oh,
for the water.
Because of the way the soil is and it's
water migration with the creek helps that heat rejection.
Is it that close to the creek?
The creek is probably about 10 feet below the actual top of the site, but based on soil conditions with their soil, it's more of a wet, clayey soil. So I mean, we'll have to put some sort of bottom fill into it, but it still can take advantage of any moisture in the dirt.
Yeah, you can't be in the creek, but they're alongside,
Right.
which is kind of using some of the site, kind of in a.
And there's actually, we talked to some people in Madison, and they said that there is no direct requirement that you have to be a specific distance from the creek. They said Milwaukee is actually in their kind of own jurisdiction with everything.
Oh, really?
Yeah.
So as long as you're on the property, you're good.
So in other areas, there might be.
There could be other areas, depending on, I guess, the location of the.
Well, then, you know how you have to also design for the other location.
Yeah.
That might be just know the answer to say if you had to ask.
And are you using a propylene glycol solution, or using just water?
I don't think they've specified exactly what would go through more efficient.
If it's primarily cooling, you might be able to get by with just water.
Well, they're 6 feet underground, so they'd probably be okay. Because my guess is in Milwaukee, the frost probably goes down to about the 5 foot level. And just to look at what Professor Walters said in a little different way, what you did with the air handling unit was very Alfred Hitchcockian.
And
That was a nice progression.
The farm, not pharma, did you, weren't you going to discount the anaerobic respiration as being kind of pharma?
Yeah, at this point too, where we have so much information that we need to, so yes, because I think it's important for us to say, we looked at these other systems, particularly because if we're doing a farm, I'm sure somebody else is going to have an anaerobic digester, and we have reasons that they shouldn't. So if we can sneak that in there somewhere and say, look, we have all this compost, why wouldn't you use this instead, instead of spending thousands and thousands of dollars to buy an anaerobic digester? We just haven't.
It looks more like Pfizer.
Yeah.
Yeah, that'd be good. Any question?
Go ahead.
It's just about the toilets and the pumps and backup energy and all that stuff. So what kind of energy is going to be required for pumping those toilets, and what is your backup? Because you lose power and you got clogged toilets.
It's really low, and I haven't thought about it. But we'll get there. I know that the rep that I talked to about the composting toilet has an answer for all of those questions. And I know that they work and that they can tie into an emergency power system, but off the top of my head, I couldn't tell you right now.
And these are waterless, or are these?
No, they have
microflush?
0.05 gallons of water per flush. So they're very low flow, which is why our reduction was 85% water reduction without the irrigation was because of the toilets.
Do they have macerators at the toilet, or is it just pumping through?
It's just pumping.
Yeah.
And so we needed that low flow because we didn't have a direct down from every toilet. So that low flow allowed us to get to that mechanical shaft on every floor.
So if you have a direct route, you don't need the water. You can still have the pump if it's going a far distance, but it has to be vertical. So if you're going in any other direction, you have to have the water associated with it.
So just for selfish reasons, for projects I'm working on, what company are you looking at for the toilets? And I want to hear more about the heat pipes.
Well, there's lots of composting toilet information I can send you. It's called Envirolet, I think. Yeah.
And the heat pipes, can y'all elaborate on those? Because that was...
The isobar? Yeah, we're talking with a company called AgriLab. They're based out of Vermont, and they have mainly farms.
No, I'm sorry, not that one.
The wraparound heat pipes?
Yes.
Yeah, so, well, it was all along the idea of we don't have an air handling unit, and so we couldn't utilize like a desiccant wheel or anything because we were trying to eliminate that. So how can we use that dehumidification? And so I think now they have stuff, it's pumped between, and usually I think it's used when you have two separate air streams that need to stay a little cleaner than the other. But they have the wraparound heat pipe, which seems like it's very effective. It has some obviously has static associated with it, which you have to account for in the fans. But the free cooling that was part of it, instead of having to cool all the way down.
And if you already have the chilled beams, then you could utilize that locally. But you need to talk about controls for the chilled beams with operable windows, and user controls and windows windows of opportunity for using the windows.
But I can send you like the manufacturers that we're looking at for their information.
And on that point about the controllers for the windows, with the heat stack, are you considering any kind of controls on those, or are those completely manually operated? Yeah. I mean, one person opens the window there without opening the greenhouse, or the greenhouse gets open, or it's open at inappropriate times. How do you control for that?
Our original thought process was that we could have some sort of sensor that said, okay, you have good conditions, you can open up the windows now. So, but that might be an unnecessary energy load. But basically right now, our intent is that they would be manually operated because
is there a green light or anything that signals?
Yeah, that's what I mean, the sensor that would...
Chesapeake Bay has a couple of those where they just have flashing lights that come on. They're like, okay, time to open the windows, and it gets everyone's attention enough to open them. So as long as somebody's in the space to open them.
But also with that same signal should send a signal to the chill beam to shut down.
Right.
Yes.
Because you may have humid air coming in, and now all of a sudden you're going to have condensate hitting the floor.
Right.
Bring in a couple of rainforest animals.
Yeah, really. Where are your cisterns located? At which level?
They're in the basement.
They're in the basement. Sorry, it just looked like they were shown on the roof, and there's.
It's
okay.
While we've been going through these presentations, I've already rethought how I want to graphically demonstrate the rainwater collection. So.
Tricky. Is the parking naturally ventilated by openings, or is it?
Yeah,
fans?
it's open on both the south and north side.
Okay.
Are
So you don't
100%
have
open.
fans.
Right.
You know, in line with what a number of other comments that have been made about reducing the number of words on the screen. Yeah. About your third slide, when you were talking about compost, you said 1 ton of active, etc. A compost generates 1,500 BTUs per hour per ton. You're saying 1 ton generates so many BTUs per hour per ton. Just leave out 1 ton of, and just say active compost generates 1,500 BTUs per hour per ton. Okay. Little things like that, you eliminate a few words here and a few words there, and it just makes it look better on the slide.
George, do they have to think about smoke evac or something for the greenhouses for any reason?
Smoke evacuation.
Yeah.
It's not an atrium. You don't have it. You've avoided three-story atriums because you've separated with your living wall the upper two floors from the lower floor. So there's no requirement for smoke exhaust system. And I think up front you need to say when you're selling the building change. You know, we've decided to change because of 3 reasons: fire protection, energy, and I forget whatever the other one was. But and to say that and to let those play out, that you've got some real reasons
and then you all
doing.
refer back to those 3 reasons as you're doing your respective presentations.
I think that we got too focused on separating all of this and not really presenting together, which is what we're obviously going to have to do in the end.
And the Living Building Challenge, if other people, whether or not other teams are doing it or not, it may be considered outside of your real primary competition. I mean, it's a benefit, so you don't need to go through too much detail of why you're doing it. And when you're talking about it, it would be less, we are committed to these 5 petals. We are doing this. This provides beauty and functionality. This provides, you know, rather than describing the system as a third-party inanimate thing, this is what we're committed to, and try to keep it really brief because that could take a lot of time compared to going through your systems.
Yeah. And be passionate about it. I'd say y'all's confidence up there was so good that I believed everything you said, whether or not.
That was our goal.
So, I had 2 things. One was with the building chimney. Is there any concern with like fire or smoke control by pulling air through multiple spaces?
No, because we can utilize, you know, I think I said transfer grow, but we can also utilize dampers. If we had a smaller boat, a fire smoke damper associated with that corridor, it could be controlled by the same sensor that would control the chill beam or the occupancy.
Yeah. And I think that's one thing we gotta just go through and make sure that we can do that. So, because you can't really return air open through corridors, so if we have that smoke transfer road, just to see if that'll count for that code.
So if you have smoke dampers, he needs to know because he'll have smoke detectors on upper floors then, which I don't think you have now.
Well, I think we specified to have them in the basement and the first floor, but that's all.
And there may be a limit. I would have to, find the source for that, and I think I gave you that requirement because we found it on another project. But it might be on how long it is, and so find the code source so you can address it.
We have a smoke damper presentation tomorrow.
Well, yeah, and the other thing was I know it's kind of already been mentioned before, but I love good graphics, and I think graphics in this presentation like really told the story. Like, there wasn't much reading that I did, which I mean it's kind of nice when you're sitting out here.
Yeah. The only thing is a couple of them put, whether it's plan or elevation, because there was a couple that I had to like look really hard to figure out what am I looking at here.
Yeah.
Good point.
What was your rationale for R30? Was that?
That's the point where the roof, there's not as significant of impact as you increase R value in the roof as there is in the wall. But at that point, it was basically the point of diminishing returns where you would have like a 0% effect after that on your cooling loads and maybe a 1% effect on your heating loads. So at that point was where you could really see that it was not worth it to go anymore.
And there hasn't really been any discussion about how you're creating a tight envelope here and what your air changes are. Your natural air changes. All right.
Yeah.
What about that?
That's also something that now that we have these systems nailed down, we'll be able to look at in depth and have clearer answers for that. But it's on our list, but until we had these systems nailed down that they would work effectively and that the cycle of the closed loop with all of the systems the energy model that we need to do by hand now because Trace won't allow us to do it will allow us to know that concisely.
So maybe you change the caption on the second goat and say, good one. and then you use it whenever the hardest question comes.
Oh wait, there's a third goat.
Of course. I should have seen that coming.
I just want to say one that's a compliment. I think you guys did like a really good job of kind of theming more towards like a story, like the way that you presented, and then even the way that you tied it to like, you know, you wanted it to be kind of like how nature acts as a system. And I think some of the other teams mentioned that, but you guys kind of more like fleshed it out a little bit better. So as you work to like kind of become one team, like that's cohesive, that might be like a good thing for you guys to kind of carry out. Like, don't hit us over the head with it, but like, you know, to mention and be like kind of clear and concise, you know, to kind of use that as like a thread throughout your presentation, because that seemed to show up, but it wasn't as, you know, like fleshed out in the other ones as it was with you guys. So I think that might be something that people will resonate with, you know, a system to a system or nature to like, you know, man-made systems or whatnot.
That's a great point, because right now it seems very siloed, which is what the whole world is trying to fight against right now, right? It's these three silos, but if you found some sort of theme that you could refer to from the previous one and make it all loop through.
You guys can help each other with the story, especially that helps with building integration and everything. So sometimes you get so into your own work, it's hard to see that story anymore, but if you can help the structural and structural help electrical, I feel like and try to find those ties between each other.
Is your design less expensive than the 5-story?
Oh, yeah.
Did you say that?
I didn't say that.
No.
We actually haven't proved that it's less expensive. But Andrea says that everyone
Let's mention it when we're talking really, really fast.
It just looks like a better plan, if nothing else. Sure does.
It's tricky for us too because there was no baseline mechanical system. They didn't even have a mechanical room, so we don't really know what to compare it to. So we're just going off. Yeah, we're just going off of if there was an air handling unit in here with the same sort of performance of what we have, what would the energy reduction be, and what would the cost reduction be?
Well, it's going to be lower cost just using common sense. Yeah. And quite frankly, you know, they're losing square footage on their top 2 floors. They're adding 2 more floors than we are just for stairs. Yeah. I mean, just circulation. They've got these long circulation quarters like 10 feet by 100 feet long on 5 floors. Well, we don't have that. We only have it on, well, kind of 2 floors, really. That's it.
Elevator all the way on the elevator was really located all the way on the north side of the site in the building, and their greenhouses were on the south side. So you had to always go all the way across the entire length.
Yeah, you need to say some of these advantages at some place briefly.
Yeah.
I know.
Well, yeah. Well, and also, you know, going to 3 stories, you encourage people to use the stairs because they don't mind walking up 3 flights of stairs. Who wants to walk up 5 flights? And just being closer to the ground where the rest of the growing operation is happening. That's all those reasons are good for a 3-story building. But cost, I think, is ultimately going to be a part of it.
Good.
Yeah, any other general comments, like critical things that we
I
need to
just think
address?
in general it was really a gutsy to redesign the buildings. That's like your thread going all the way through. And just tell the story without criticizing the previous designer and take that.
Because they may be the judges.
Right. and get excited about what you're doing you're being innovative and why, and weave it through. So that just pat yourselves on the back, you did a good job.
Yeah.
You're ahead of it. You're ahead of it.
Thank you guys.
Yeah, good.
Thank you.